Good morning. Thank you for joining us. I see some of you are helping yourselves. We have donuts and watermelon and drinks in the back. Go help yourself. Go run back there now if you need to. Welcome to the second day of the National Weather Center Research Experiences for Undergraduates program. Final talks. Today we have presentations from the NWC REU and AI2ES, who has partnered with the REU this summer. My name is Alex Marmo. I'm the co-director of the NWC REU program, and I run it with Dr. Daphne Ledoux, who has been an amazing asset to the program for over 20 years. A little bit of history of our program. It's funded by the National Science Foundation, and NSF has been funding REU programs since the 80s. Our funding began in 1991 and was led by Bill Beasley and others from the School of Meteorology here at OU in partnership with NSSL. Since then, we've had over 270 students come through on 8 different REU grants. These programs are a fantastic way to bring bright undergraduates from around the country to join our organizations and see what research is really like. And this year we have 14 NWC REU students and 5 AI2ES students from across the US. And I'm very glad to have you joining here in person and online. A note to our audience, this will be a conference style AMS format with a 12-minute presentation followed by 3 minutes of Q&A. So please hold all of your questions until the end of the talk. And also the online folks were a little bit quiet yesterday. Definitely feel free to raise your hand or unmute. We'll be monitoring that too. To our students, these talks might seem a little bit scary, and I'll try to make the same joke as I did yesterday. I'm nervous for all of you, but you're going to do fantastic. The scientific presentations are a great way to show how you've learned throughout the summer, and this is a safe space. You're here to present what you found. You've only been doing this for 9 weeks. You can't know it all. You can't do it all in that amount of time. And now I will hand it off to our moderators, who will do introductions for the students before we start presenting. Thank you.
Maybe you've seen it driving down the road, and you'll see the sign, and got it, and and got it. Just in case you want to know, this recording. But bridges, ice before roads. You've probably seen this driving down the road. Keep this sign in mind because this will provide the foundation for what I'm talking about this afternoon. So exactly why do bridges ice before roads? There's a couple of things that go into play. Because bridges are suspended, there is more surface area that is exposed to air temperature. They have not just the top, but also the bottom of the bridge is exposed, as well as the sides. Compared to roads, who have just the top exposed, and they also have extra insulation from the ground. So they have that extra heating from the earth, able to keep the temperatures a little bit warmer. So this leads to situations like this, where there's accumulation on the bridge, but there is no accumulation on the road. There are a few other factors that come into play: how much sun is hitting the roads, how many cars are traveling, as well as how much heat is actually being absorbed into these surfaces. So why am I talking about this afternoon? Winter weather plays a really big factor during the winter season on adverse road weather conditions. Back in 2015, Black and Moat released a paper that had this diagram of weather-related fatalities in the US per year on average from 1996 to 2011. Compared to all the other factors like tornadoes, heat, winter-related aviation, winter-related motor vehicle accidents really stand out with an average of 817 fatalities per year in the US during that time span. So the National Severe Storms Lab decided they were going to help predict when roads are subfreezing by creating this model. This model was introduced by Handler et al. In 2020 and is known as the probability of sub-freezing roads, or the PROBSR. This provides accurate and efficient probabilities for sub-freezing roads across the continental US. As you can see from this graphic, the darker purples indicate a higher probability that the road surfaces are below freezing, while the lighter colors of white and light blue indicate lower probabilities. There are some criticisms for this model. First off, this model assumes that all roads are made the same, in that it does not discriminate between road and bridge surfaces. So the big criticism is that it underpredicts bridge surface temperatures. Well, these 2 bullet points are the main objectives for what me and my team did this summer for our research. So where do we get this information from? We got it from a network of systems called the Road Weather Information System, or RWIS. These are found in most states across the US. Some don't have these, but they are run by each state's Department of Transportation, and they consist of 2 components: an RWIS tower that collects air temperature, humidity, wind speed and direction, as well as visibility. And then an RWIS sensor that are these really tiny, they kind of look like hockey pucks that have just been put into the road. They take road surface temperature as well as pavement condition. So to start our research, I mean, obviously the sensors taking data directly from the road, might as well start there with that data. So for which stations that we looked across the state of Ohio, and we looked at 17 RWIS stations. We examined hourly data from the previous winter season from 2022 to 2023. Now, we chose these 17 RWIS stations because they each have 2 sensors, one for a road and one that's on a bridge. Now, the problem is that there's no metadata that classifies which one is which. So I had to do the very fun fact of manually identifying road and bridge temperature sets. It was a long process, but had to be done. So once we got those identified, we can now compare road and bridge surface temperatures directly to each other to see if there are any correlations. This diagram shows bridge surface temperatures on the y-axis and road surface temperatures on the x-axis. As you can see, at colder surface temperatures, more often roads are warmer than the bridge. As you can see, the blue plots, those blue points, they're below the 1-to-1 trend line, which indicate that road surfaces are warmer than the bridge surfaces. However, as the surface temperatures increase, it gets a little more, or I guess I should say less systematic. So there's equal parts bridge is warmer, equal parts road is warmer, and they kind of fall on that 1-to-1 trend line. Now, for what we focused on was at the left side of the spectrum, where we have our at freezing and below freezing temperature sets. So we know from the sign that bridges tend to ice before roads. So the next question we wanted to know is, how often are bridges below freezing while the road is above freezing? This leads me to this contingency table. On the top, we have bridge surface temperature, and then we have below 0 degrees Celsius and above 0 degrees Celsius for our below and above freezing respectively. And then on the side, we have our road surface temperature, negative 0 degrees Celsius being below, above 0 degrees Celsius being above. From these cases that we collected, there are a total of 6,310 cases. 3,971 of them are where both the bridge and the road are both below freezing. This takes into account about 63% of the cases that we examined. A much smaller amount of 22 are where, oddly enough, the road is warmer than the bridge. Obviously, this is rare, but it's around 0.3% of the cases we examined. But for our question, this was the more important number. 2,317 of these cases are where the bridge is below freezing while the road is above. This takes about 36.7% of the cases that we got. So obviously the conclusion that we made is if one is going to be below freezing over the other, it's going to be the bridge, most likely. Now we looked at other bridge identifiers. For example, we looked at time of day, if roads and bridges behave differently in the morning compared to the evening time. We looked at their differences by month. Obviously, November temperatures are going to be different from February temperatures. We also looked at latitude, how far north are this RWIS data coming from. We even compared it to model surface temperatures from the HRRR. And we did a statistical analysis of bridge and road temperature averages, looking at how those averages skew, as well as looking at the kurtosis to see how the outliers play into those factors. Sadly enough, we couldn't find any definite signals or trends with these factors. So we kind of had to go back to the drawing board, but we looked at sensor data. Then we thought, let's look at the data from the RWIS tower, and more specifically, the air temperature that those RWIS towers collects, and comparing those to the bridge and road temperatures that we also have. So this diagram shows on the y-axis, it's the bridge air temperature difference. So it's the bridge surface temperature minus the air temperature in degrees Celsius. And then the x-axis is divided into categories by 5 degrees Celsius of the air temperature. As you can see for bridges, in extremely cold cases, bridges can get honestly up to 6 degrees Celsius warmer than the air temperature, but this is at very extremely cold cases. The ones we're more concerned about is from -15 to 15 degrees Celsius. As you can see by this line, the median air temperatures kind of follow this straight line in between -15 to 15. This shows that for the most part, bridges remain slightly warmer than air temperatures, right around 2 degrees Celsius. So they really don't deviate far past below freezing and far past above freezing. Roads, it's a slightly different story. We did the exact same thing. Obviously, at higher, or at least at colder air temperatures, roads can get significantly warmer than air temperatures. In rare cases, up to even 13 degrees warmer than the air temperature. But again, those are rare. We looked at the -15 to 15 range, and instead of the straight line that we got with the bridge, notice how the road, there's almost this negative trend that as the air temperature increases, that difference between road and air temperature decreases. For us, this was good because we found a definite signal, and there's a slight definite difference in road and bridges and how those temperatures behave with air temperatures. However, the problem that we have is when forecasting winter weather events, the important time is right around about freezing. This is when rain starts to turn into ice, into freezing rain. So we want to look at those and see if there are any big differences. But as you can see, the air temperature differences for bridges, it's like slightly below 2.5. For roads, it's slightly above 2.5. There's not much of a difference. So it's a little bit inconclusive, especially during that critical time. So what we've learned from our research is that when surface temperatures are cold, roads tend to be warmer than bridges. When air temperature differences provide some insight into differentiating between road and bridge temperatures, especially in sub-freezing conditions. However, the more important case, when they're at freezing, there's little contrast in air temperature differences between roads and bridges at freezing. So what we want to look at in terms of future work is look at RWIS data in other states. Obviously, there's more states than just Ohio. We can also examine data from other winter seasons. We don't have just to look at last season. Do more bridge identification, which means more bridge data. There's more to work with. And we can investigate new variables like elevation and wind speed. And with that, that concludes my presentation, and I will take any questions at this time. Thank you. Yes.
Would something else that you consider looking at be how the bridge is constructed?
Yes. So what I found in my research is that most roads are laid with asphalt, which is, has that darker color, and so it tends to absorb more heat. While bridges are constructed more likely with concrete, which is a more flexible material. It's good with dealing with, lots of weight on it. But it is a lighter color, which means it has a higher albedo. And if you don't know what albedo is, it's a tendency to reflect light. And so the way concrete doesn't absorb as much heat as roads do. So that is another important factor when it comes to those temperature dynamics. So yeah. Yes.
Did you look at those outlier cases, the 22, where the bridge was warmer than the road?
Yeah, it's a little weird, isn't it? It's a little weird. We did. We would like to go into that a little bit further, just because we didn't really have a lot of time to really delve into those cases. We really wanted to look at, when bridge is below freezing while the road's above. Obviously, that was the point of our project. But it is very interesting that there were a few cases. The ones that we did look at, it did seem more like it was an error in the sensor measurements. There is one case that was a little strange. It was during a holiday blizzard back in 2022, right before the Christmas season, where the road did happen to freeze before roads for a couple of those stations. Again, really couldn't glean into that much. I mean, the fact that we even found that was weird. So we didn't have time to really delve into weird cases, but that would be something that we would love to look into. Any further questions? No. All right. Thank you so much. Thank you.
All right, so next up, we will have Ethan Stewart, who is a junior studying atmospheric sciences and mathematics, double major, from Indiana University in Bloomington. He'll be talking to us about comparing differential reflectivity arcs using phased array and conventional radar data. So yeah, go ahead and take it away.
Thank you so much for introducing me, and I'm going to toss us right on in here. So here is some radar imagery from our conventional radar up in Oklahoma City of a supercell from April 23rd, 2022. The signature of interest for this study is this guy here in the differential reflectivity, this region of higher differential reflectivity values. So I want you to take a mental screenshot of this, because now we're going to look at the same image but with our new type of radar. And here we have it. We have the signature again in the same spot, but it looks a lot cleaner and smoother with this new type of radar. Again, just backing up, this is what we currently have, and this is our new type of radar. And that kind of gets at the goal of my project. I'm seeing how the signature appears and evolves with our new type of radar compared to what we currently have. So now I'm going to back up, stop being vague, and talk about what's going on here. We're going to go in a deep dive of radar history ever since the 1930s. I'm just kidding. We currently have the WOSR-88D system used by the National Weather Service in forecasting. These guys have been around for quite a while, and ever since 2013 have had dual polarization capabilities. The radar beams with these guys are steered around mechanically, as you have a dish that physically rotates around. And while they've been great tools in nowcasting and saving lives, their lifespan is expected to end around the year 2040. So researchers, especially here at NSSL, have been on the hunt for a replacement. And one candidate for replacement are phased array radars. With these guys, the radar beams are actually steered electronically. So it gives the operators control over having faster full volume scans and or more dense vertical sampling of the atmosphere, a product of the more adaptive scanning that phased array radars bring. And thank you very much to the Advanced Technology Demonstrator, or ATD. We finally have our first chance to look at the dual polarization capabilities of phased array radars. This is the radar that we toured the other week, and it had that really nice air conditioning, and it was very lovely. So the signature we are looking at are differential reflectivity arcs. Differential reflectivity is simply just a measure of the difference in return power in the horizontal channel and the vertical channel of a radar pulse. So objects that are larger in the horizontal, like larger raindrops, are going to have higher ZDR values, while objects that appear more spherical to the radar, like hailstones, will have ZDR close to 0. And ZDR arcs are defined as regions of enhanced ZDR, typically at or above 3B, so larger raindrops, that are usually found along the low-level forward flank reflectivity gradient in supercells. For me, that's a lot of words, so I like looking at this graph down here, which does very nice in showing where ZDR arcs typically are in supercells. And these are our main dual pole signature of interest because they have some important implications. If a ZDR arc is present in a storm, it means that the storm is undergoing size sorting. And size sorting is pretty much exactly what it sounds like. Your larger raindrops are getting separated from your smaller raindrops as they fall to the ground. And this happens as a result of your storm relative wind profile, which should look something like the figure here. So what happens is your larger raindrops with larger terminal velocities will pretty much fall straight to the ground after exiting the updraft, while your smaller raindrops are going to get lofted by your storm relative winds and infected further into the storm before they reach the ground. So you get this nice separation of hydrometeor size at the ground, and thus our ZDR arc. And in the presence of a ZDR arc, we should be on the lookout for potential low-level mesocyclone intensification or formation, if not already present. And these ZDR arcs can get disrupted by hail cores when we have hail that physically falls within our arc. And that can imply the presence of potentially colder, more negatively buoyant downdraft air existing near our updraft region. So the goal with our project is to compare ZDR arcs between the ATD and KTLX, which is that conventional radar up in Oklahoma City. To do this, we're looking at two cases, April 23rd, 2022, which we just saw imagery of, and May 11th of this year. Both these cases contain tornadic supercells with accompanying ZDR arcs. And to look at these, we're doing them both qualitatively and quantitatively. Qualitatively, I went through both radar data sets and noted the biggest differences between the two, trying to find what one radar was communicating that the other wasn't. And then quantitatively, we used the Supercell Polarimetric Observation Research Kit, or SPORC, which rolls a little more nicely off the tongue, to go through, it's a Python package, and extract out a bunch of ZDR arc traits with time, such as their areas, means, medians, and standard deviations. So we're now going to hop into some results. I've compiled here what I think are the biggest differences. Obviously, I would love to talk for 4 hours about all the differences, but we'll just try and go through the main ones here. So here is a screenshot I have of one of the supercells from our May 11th case. On the top, you can see the ATD data, and on the bottom, you'll see the KTLX data. And I'll keep that consistent throughout the presentation. So in this screenshot, we can see the supercells both have ZDR arcs. However, the ZDR arc with the ATD is much cleaner and smoother than KTLX. In KTLX, it's really difficult to tell where our arc begins and where it ends within the storm. You can also see the gradient of ZDR in the ATD data much better as you go deeper and deeper into the supercell, which is giving us more confidence of that size sorting going on within our storm. And kind of along the same lines here, we have the same supercell, but a little later on. My little bullseye here in these pictures represents an ongoing EF0 tornado. And again, same story with our ZDR arcs. They're both present in the radars, but the ATDs is much cleaner. And we can also, with the ATD, get this line of really fine, higher ZDR wrapping around into the hook echo. And with KTLX, we kind of get the same up to a point, but getting deeper into the hook echo, it just gets really noisy. And this isn't something that I just noticed with the 511 case. Our April 23rd supercell also showed the same thing. Similarly, we have ZDR arcs in both radars, but with the ATD, we get this nice line of higher ZDR wrapping around into the hook echo. But with KTLX, we don't really get that. We just get a bunch of noise. So changing gears a little bit here, we're going to go into story time. The April 23rd supercell ends up dropping 2-inch hail. So I want to go through and watch the descent of this hail core with both radars. So this is the first scan with the ATD at about 3.2 kilometers where it notices the hail core. 1 minute later, at 2.4 kilometers, the ATD sees the hail core here. And shortly after, at 1.9 kilometers, KTLX finally gets its first scan of this hail core and recognizes that it's coming down. It's a little noisier to see, but you can still make out that area of near zero ZDR. And then at 1.4 kilometers, not too long after that, the ATD picks up the core at 1.4. And then a minute later, the ATD picks up the core at 0.6 kilometers, which is its lowest elevation scan. And then a minute later, KTLX picks up the core at its lowest elevation scan. So just to summarize these past few slides, because that was a lot, the ATD was able to see that core aloft and watch it transition all the way down, while KTLX didn't really see it aloft, caught it in the middle, and then caught it right at the end a minute later than the ATD. So the ATD had a much easier time watching the descent of that core, which is cool and all, but why am I talking about a hail core? In both radars, these hail cores go on to produce ZDR arc disruptions, which show up very nicely with both of these radars. You can see this large area of near zero ZDR in both radar datasets, which is literally cutting into our ZDR arc. However, the radars start to differ when they show this arc disappearing, the disruptions disappearing. So at 2342 UTC, you can see that in the ATD, we have a stream of higher ZDR values starting to creep back into this hail core and try and reach the other side. Well, in KTLX, we don't really get the same. We still just have this general large area of near zero ZDR. Fast forwarding a few minutes at 2345 UTC, it's pretty clear at this point that we have a nice continuous stream of high ZDR and ATD. So our disruption is pretty much over. While in KTLX, it's really difficult to say. In my opinion, I believe this is still a disrupted arc because I don't see a nice stream of continuous high ZDR values until the next scan at 2046 is when I would say the arc is back in KTLX. And this is important because this longer time that the arc is disrupted in KTLX would imply a longer amount of time that we could have colder downdraft air existing near our updraft region. And now to finish off my presentation, I want to talk some numbers. So here is a graph of the ZDR arc areas that I have generated from SPORC for the April 23rd supercell case. Each data point on here represents a full volume scan interpreted by SPORC. So with the ATD being the blue line and the KTLX being the orange line, you can immediately see the increase in temporal resolution that comes with the ATD. We have a lot more data points to work with in a shorter time frame, which allows the ATD to be able to see finer scale changes with our ZDR arc with time. While in KTLX, you get updates every 6 minutes, so the arc can be a little jumpy. And looking at the same thing with the 511 case, here's the same graph for one of the ZDR arcs, but 511 is a little goofy in that its ZDR arcs can get very elongated at times and take smaller values. So SPORC actually struggles to pick up the entire arcs with both radar data sets. However, this graph here shows the ATD data being much easier for SPORC to read. We can see that the areas here with the ATD data are much more representative of an arc, getting into like 20 plus kilometers squared, while KTLX shows these really small areas for our arcs that aren't truly representative of what they look like. And also, KTLX at this point around 2350 should have a data point. SPORC should have been able to recognize the ZDR arc, but due to the KTLX's data quality, it could not. Well, it could with the ATD. So jumping into our conclusions, we knew walking in that the ATD offered us better dual pole data quality and increased temporal resolution. So that translated to allowing me having an easier time detecting ZDR arcs and small scale features like our high ZDR wrapping into our hook echoes. It also allowed me to see rapid evolving dual pole signatures, such as the descent of our hail core. And finally, with our SPORC output, we have hints that auto-detecting algorithms may have an easier time identifying signatures with ATD data rather than conventional WSR 88D. And with that, I will take any questions. I'm sorry, I threw a lot at you. Yeah.
When you were showing your first case, the April case, why do you think the ATV had larger VDR arcs later in time than the other one, but it had smaller VDR arcs earlier? The one before this one.
One before this one. That's a great question. I am not honestly sure 100% how Spork and that Python package works, but I do know that KTLX is a lot more sensitive than the ATD. So things like debris and bugs that get kicked up front, like in our forward flanks, often cause KTLX to have really high ZDR values that aren't truly a part of the arc that I think Spork might be picking up on. Well, that's not really present with the ATD, so it results in those initial lower area values. Does that answer your question?
I just think it's interesting that it's living from being lower than higher.
Yeah, this higher thing might be a result of our temporal resolution too, since KTLX only sees this point right here and this point, while the ATD, we have a finer temporal resolution. So if the ZDR arc is truly getting bigger, it just might be something that the ATD is seeing and KTLX isn't.
I suppose it's also the case with this graph, that the reason that the KTLX arc seems to be receiving the other one time is the resolution of the core here, so it's going to see these areas is bigger because the grid boxes are bigger. Is that could that be why you're, it seems like the ATD is flat and behind.
It could be. That's something that I would have loved to look into had we had a few more weeks here. Unfortunately, we don't have time to fully go through how Spork is operating on these, but that would be a wonderful area to do for future research on. Any other questions? Thank you.
All right, so next up we'll have Corey Schultz, who is a senior at the studying atmospheric and environmental sciences at South Dakota School of Mines and Technology. He'll be talking to us about the investigation of lightning and storm electrification processes using a phased array radar and the lightning mapping array. All right, go ahead and take it away.
All right, thank you for that introduction. So first off, I want to talk to you guys about what lightning and storm electrification is and how it actually works. So I'm going to simply break this down to storm electrification is the separation of charged particles in or around the updraft of a thunderstorm. So in our study, we're looking at, or we're using an all digital mobile phased array radar, HORIS, to look at range height indicator scans, or RHIs. And in those RHIs, we're looking at specific differential phase, or KDP, and differential reflectivity, or ZDR, to look for ice crystal alignments within that storm. So let me break down all those terms for you, because not everyone probably knows what those things are. So our RHI is just a vertical slice through a thunderstorm, which is what you can see in the figure on the right. Specific differential phase, or the KDP, tells you the difference between horizontal and vertical hydrometeors, or in this term, ice crystals. So we're looking for negative values for that. And differential reflectivity is what Ethan was talking about last time, where the difference in horizontal and vertical beam returns from the radar. And that we want to look for negative values as well, or we'll also take near zero values. So the last thing that we're using is the Oklahoma Lightning Mapping Array, or OKLMA. This tells us, or this shows us, excuse me, this shows us the location of flash sources in a thunderstorm. So if we look at this figure on the right, and we look at this area that's circled in black, we can see that the near zero or slightly negative value of specific differential phase is in that light tan color, and the black marks above and below it are the LMA data. So what is the current problem? Well, current radar scan times are around the order of 5 minutes for a full volume scan, which is far too long to pick up on electrification processes, which take on the order of seconds. So our solution to this is we're using a phased array radar, which hopefully can scan at times fast enough to pick up on the breakdown and buildup of these electric fields within the ice crystals. So in our principal objectives in this were, do we see alignment signatures evolution? And does this line up with the three-dimensional flash locations? So let's take a step back and look at what's already been done. So as far as LMA data goes, the first LMA was put in place in 1998. This system accurately located VHF, or very high frequency radiation, from lightning discharges in and around the thunderstorm in 3 spatial dimensions and in time. And then moving forward to 2004, the accuracy of the LMA was tested and the low uncertainty was found when a storm was in 200 to 300 kilometers in multiple sensors. So if we look at the figure on the right, this shows us the areas of the OK LMA site locations, and the purple indicates the 3-dimensional space, and then the orange is the 2-dimensional range. So if we moved on to the phase array radar, the early 1960s, this is when power technology was first implemented, but not until 1997 did a power technology get implemented for weather purposes, and that was put on the Navy destroyer. So if we move forward to today, looking at Horse's advantages, it has beam agility, adaptive scanning, and it's all digital. All of these things are making this the most advanced radar technology into today's time. So as far as our data is concerned, we're looking at the May 11th case as well as what Ethan was looking at, which is that Central Oklahoma tornadic supercell. So as far as the Oklahoma or the OK LMA data is concerned, we looked at it from 6:30 to 8 p.m., where there is over 22,000 flashes detected. And as far as Horace's deployment is concerned, I'm not going to bother going through all that stuff. You guys can read it if you want. But I'm going to point out to the fact that there was just over 2,000 RHI scans in that 1 hour and 18-minute period. So it was very high scanning rates. So as far as our methods are concerned, we had to create a code to plot both of the Horace data and the LMA data, combining together to look for that rapid crystal alignment and see if that was actually captured. KDP was calculated using the Volpiani method, and then the LMA tools method for flash sorting was used to determine the number of flashes in the storm. And then we also shrunk down the time to the specific time just for better purposes as far as studying. So as far as storm overview goes, well, we'll just run with it. So as far as storm overview goes, you can see this is a small squall line with that embedded supercell. The storm's relative motion is to the north-northeast, and it's roughly moving at 29 knots. And seeing Horace's position, you can see it in lat longs, and the azimuth is 270 degrees. This should be moving. I don't know why it's not, but just picture the storm is moving to the north-northeast. And during the scan time, this is roughly 22 minutes. So moving on to the vertical ice alignment, negative KDP values indicate ice crystal alignment, or they can. This has been proven in past research papers, but looking at our study, we unfortunately did not see this buildup and breakdown detected. So because of that, we also looked at the near zero ZDR values for the storm. And we saw some potential looking at those values with the LMA data. So looking at this image, it's a little hard to see. So we'll move on to this animation, which is not working. That's fun. Okay. So just picture this is moving in time. This circle, the light blue area, would show us that the KDP, which would be in the light gray, is never actually dissipating. It moves around, it goes in and out a little bit, but we never actually see the loss of the negative values, which is what we would want to see. So because of that, we also looked at the differential reflectivity. This area, we see the overlap of the LMA data along with the light or the dark blue colors, which is the near zero. And one more thing to note is all of these dots for the LMA data are within the 3-kilometer span of the RHIs. So finally, moving on to flash propagation, and intensity. Both of these were well defined by the OKLMA due to the storms being directly over the central Oklahoma LMA sites. And just one thing to note is that there was just over 1,300 unique flashes within this 22-minute period. So if we look at this figure on the right, this is a top-down view of the storm, looking at the KTLX scan. And the blue dots are all within the 3-kilometer distance of the RHI, whereas the black dots are outside of that zone. So this figure alone, just from one scan, shows 5 unique lightning flashes. So we'll move on to the intensity and just look at how intense this 22-minute period was. So just setting up the graph, flash count is on the y-axis, time is on the x-axis. If we look at the first third, roughly, of this chart, you can see that the average flash count is roughly 2 to 6, which shows us a drastic increase in that flash density. And then at one time, it does make it up to 10 flashes in one scan, which is a lot of flashes for 2 seconds. But as we move farther along in the chart, it looks like the storm is dying or decreasing, but that's not the case. This is just that the scan angle is consistent while the storm is moving to the northeast. That's why our flash numbers decrease slightly. So let's wrap this all together. The KDP values did not represent the buildup and breakdown of the electric fields like we were hoping to see. So we came up with a few hypotheses as to why this was. So the first one was Horus's scan times. Is Horus fast enough to capture these? That's one future research topic that we may go into. Second is the high flash rates. Do the high flash rates not allow ice crystals to align properly or disalign? That's a whole nother story to look into. And then finally, the Horus's beam width. Because Horus is new technology, the beam width was wider than a pencil beam. So this may have overloaded the radar and had too much information coming back to it. But we also noticed that ZDR showed promising signs of determining regions favorable for lightning propagation. And then the OKLMA also showed us a very detailed 3-dimensional map of the storm's flash propagation and intensity. With that, thank you, and I'll take any questions.
Comparison for the standard radar to see if you could see it in those scans as well?
No, just the Horus.
So my local neurology background is not usually strong. But I do think negative KDP or negative CPR were typically plausible observations. So if there are really more artifacts of noise or miscalibration of the instrument, so I'm a little surprised to see it exploited here. What's happening there that, I mean, what is it about the negative KDP or the negative CPR that's physically attached to it? What's going on? Basic connecting to light. I don't understand.
So the negative values, as far as KDP goes, negative values show vertically aligned ice crystals in this case.
Okay, so KDP is different from PDP, and PDP is not as constantly increasing or level as you move away from the radar, say from the noise. And so when you get a negative value, that's noise that's coming back.
I mean, there will be noise, yes, but that's also one way of determining the orientation of what it's
So
hitting.
you're getting you're using the noise and you're exploiting the noise of the system to understand something like that.
Yeah, like like ice crystals will align, right? You like feels that they're pointing and the
Depolarization.
Mhm.
Okay, Oh, yeah, that's what came up in the radar.
Yeah.
At this moment. Right. Okay, I'm sorry, I just didn't
Yeah.
understand, so,
Mhm.
thank you.
No problem. Any other questions?
You have more time this summer, would you be tempted to look at other storms?
Yes, that's a major factor. Only working with one storm, very hard to actually make accurate. Yes, and then a whole nother situation is the beam width. Because having a smaller beam width in theory will make it better data, and we possibly will pick up the signatures that we're looking for, so.
There was my curiosity for, but what are you deployment limitations for? It's like how, like, if the storm is approaching and say, you don't want to get forest failed on, like, how?
That's the case.
You gotta get out of there, like, how close do you allow it to approach? you?
Horace on this case was just deployed in the parking lot of Lloyd Center. So Horace hasn't really gone too far into the field, because it's also, you need a semi license to drive it, so. Yeah, limitations they're up there. It's not a radar you would drive onto the back roads.
Right now, I think it's also because it's deployed during the day, during business hours, because the cars can't fit here, so rather
There's that as well.
can't go whatever you want.
A lot of limitations, and it's new technology.
Good, thank you.
All right, so next up, we will have Walter McGavran, who is a junior studying mathematics and physics at the Loyola University in Chicago. He'll be talking to us about characteristics and statistics of tropical cyclone tornadoes and warning skill. All right, take it away.
Thank you. Hello. So I want to start just with some background on tropical cyclone tornado genesis. If you look at the plot to your right, this is a scatter plot of tornado locations relative to the motion of tropical cyclones. So you can see that the majority of tornadoes are formed in the right front quadrant relative to the cyclone's motion, and the majority occur 200 to 400 kilometers away from the center of the cyclone. This arrow indicates the forward motion. It's not specifically understood why this distribution occurs across all tropical cyclones, but it's believed that it's because at this area there is a strong enough combination of vertical wind shear and cape so that you have enough vorticity and air partial buoyancy to create these rotating supercells that result in tornadoes. Yet, despite this, there are still plenty of forecasting challenges associated with accurately predicting these tornadoes. If you look at this plot, which shows a track of Hurricane Isaias from 2020, segregated along 6-hour intervals, you will see that indeed many of the red triangles, which represent tornadoes, form to the right front of the track, along with the tornado warnings. You'll also take note of the fact that as the TC makes further landfall and extends deeper into the country, the warnings become more scattered and less correlated with individual tornadoes. This is because they are difficult to diagnose on radars. The updrafts are shallower for these supercells, and the mesocyclonic diameters are also much more compact. So seeing them via radar is difficult, especially when they're embedded within the rain bands of tropical cyclones. Additionally, observational data is limited because most reasonable people don't go out in the middle of a landfalling hurricane to try and see tornadoes. It's not normally recommended. All of this compounds into some issues actually forecasting these tornadoes. Now, you may be asking yourself, why don't you just spread warnings everywhere in an effort to get the most coverage for tornadoes? But this is an issue for a couple reasons. One, the call to actions for tornado warnings are often conflicting with the call to actions for other hazards associated with tropical cyclones, such as flash flooding. And additionally, if you're wrong frequently enough, people stop listening to you when you're right, which is an issue. So what studies have been done to quantify warning skill for tropical cyclone tornadoes? Unfortunately, not a tremendous amount. There have only been about 2 case studies examining individual tropical cyclones and their associated warning skill. Most notably, Hurricane Harvey, which hit the Houston metro area in 2017. Some of the notable takeaways from this study were that warning skill was lower overall at night, and Harvey is notable for its rather robust percentage of tornadoes formed in the evening hours, 38.5%. If you take a look at this plot, which shows 3 warning statistics that I'll get more into in a bit, you can see that the best holistic warning came 200 to 400 kilometers away from the TC, which is good because if you remember, that's where the majority of tornadoes form. So you're hitting where you need to hit. The study also used radar characteristics to evaluate potential forecasting thresholds to be used when distinguishing between tornadoes and non-tornadic rotating cells within rain bands. The primary characteristic used was rotational velocity. So this is kind of where my project starts. As opposed to looking at individual cases, I looked at a decade's worth of data comprised of 43 different tropical cyclones, 557 tornadoes, 2,381 false alarms. It was built off of the SPC's tropical cyclone tornado data set, along with hurricane track data from the National Hurricane Center and NOAA archive radar data. Additionally, the radar data that I was specifically looking at was maximum azimuthal shear for tornadic and non-tornadic rotating cells derived from 0.5 degree tilts. Primarily, I was looking at 3 warning statistics: false alarm rate, or FAR, probability of detection, or POD, and critical success index, CSI. If you take a look at the contingency table, you will see the observed and forecast binary options where you have yes or no for both. Probability of detection, which is a ratio combining accurately warned tornadoes versus all observed tornadoes, as well as false alarm rate, which is the ratio of false alarms to all warnings given, including those that accurately hit tornadoes. Now, CSI is not depicted especially well here, I think, because it's more of a function of both POD and FAR, which allows it to be more sensitive to both tornadoes and warnings, which can be used for a more holistic view of warning skill. And in addition to this, because it's a function of both POD and FAR, you can use it as something of a tuning measure to evaluate, do you need to scale up your warnings to hit more tornadoes, or are you warning too much and you're now outweighing the benefit of actually hitting these tornadoes? Additionally, my radar data I use to differentiate between hit and miss confirmed tornadoes, as I previously said, and non-tornadic rotating cells. So some of the results that I found, I will begin to discuss, beginning with variability of warning skill as a function of distance from the TC center. Now, as you can see, unlike in Hurricane Harvey, the warning skill for CSI, which is the black bar, was actually lowest 200 to 400 kilometers away from the TC center. And indeed, probability of false detection, or false alarm rate was highest from 200 to 400 kilometers. In addition, POD stayed relatively the same. The numbers above each bar are the sample size associated. So the number of warnings are above the red bar, which is false alarm rate, and the number of tornadoes are above the blue bar, which is probability of detection. You'll also notice that in accordance with historical data, the majority of tornadoes and warnings did fall from 200 to 400 kilometers from the distance of the TC center. And you'll notice as you move beyond 600 kilometers from the TC center, your warning skill starts to drop off quite steeply. And as you get to 800 plus kilometers, over 10 years, only 8 tornadoes formed, and yet 148 warnings were issued. That's a false alarm rate of 97%. It's not very good. So there is some artifact going on here that suggests that either forecasters are more wary this far out, or the resolution from radars is no longer very good at this distance. Additionally, I looked at variability of warning skill relative to local sunset time. And as you can see, as opposed to what has been previously found, particularly with the case study with Harvey, warning skill after sunset is not quite as bad as you would expect. In fact, it's slightly above what you would see for right before sunrise, which is interesting, I think. You'll also notice that, again, 6 to 0 hours before sunset, you have the majority of tornadoes and false alarms forming. You also have, at that point, the highest warning skill as defined by CSI, which again, I think is interesting. And some of this may account for a new radar strategy known as SAILS, which oversamples the lowest radar scan, which provides better resolution at night and allows for a higher warning skill when normally observations are limited. Lastly, I looked at variability of warning skill relative to actual cyclone intensity, which was defined by their maximum wind speeds. So as you can see, tropical storms form the majority of tornadoes. And this is partially because storms spend the most time as tropical storms after landfall. Even super strong hurricanes decrease rather rapidly after crossing the coastline, which is why you see such low populations for hurricane level winds. It's also notable that tropical storms have the lowest warning skill, which is in part because they exist most often in locations that have offices that are less familiar with either tornadoes and or tropical cyclones. Stronger storms do, however, demonstrate a higher ratio of false alarms to tornadoes, most likely a product of the higher sensitivity that forecasters have for these strong storms. It's pertinent to get as much information out as possible, especially given how damaging these very strong storms can be. And then for radar, I looked at azimuthal shear, which is essentially a metric of rotation for storms. And as you can see, for forecast tornadoes, the median is significantly higher than missed tornadoes, which I think is quite interesting. You'll also notice that the extreme values tail off as you go along, hits, misses, and non-tornadic rotating cells also found within rain bands. So the distribution is also shifted up. So where the most values occur, you'll notice that for hits, that's around 0.01. For misses, it's around 0.008, which suggests that azimuthal shear, should it ever be integrated for operational forecasting, could be a useful metric. So now, to summarize, my study was considered a decade-long data, and some of the key points were that warning skill falls outside of 600 kilometers. Nighttime warning skill is stronger than was suggested by historical records, which may be, again, related due to advancements in radar technology and strategy. Strong TCs generate fewer tornadoes, most often due to the fact that they last for a shorter period of time over land. And to fix some of these limitations, other radar characteristics such as azimuthal shear or divergent shear, which is a metric looking at convergence, could be used to fix some of the limitations associated with rotational velocity, which suffers from data degradation at long distances from radars.
Did you guys look at the variability of warning skill relative to like distance to radars?
Yes, and that you do see greater variability. closer to radar's warning skills higher, which you would expect given that a lot of radar characteristics currently in use are related to their distance from the radar.
Okay.
So you're showing that tropical cyclone plans are challenging to forecast. So what next research steps would you recommend to do operationally focused research to alleviate that?
I think, quite frankly, a lot of it has to do just with radar advancements and using different radar characteristics eventually, and that could be 7 to 10 years down the road. But observational data is so limited, especially as these TCs make initial landfall, and there's so much going on, especially with flooding and surges, that you need to, one, become, I think, you need better radar thresholds to make these calls. And I also think understanding the different trends associated could be useful. Like, obviously, there are 148 warnings given out for tornadoes quite far away from the center of TCs, and yet there were fewer than one tornado per year in that area. So probably you could just avoid hyper focusing on those areas.
That question that you said, Charles, I thought this was a good application for the climate vision radar. So if you're showing that the closer that you are to the radar, the better the warning skill is, then the supplemental commercial radar networks that are coming online, they have a lot of value for this kind of application. It's really interesting to see if you can get the same kind of, if you can see that same kind of performance by using a radar that's only, repetitively scanning the field not 5 degrees over and over again. You don't have the whole more, but that was really interesting.
All right, so the last talk before our quick 15-minute break will be Stephen Reardon. He's a junior studying atmospheric sciences at the University of North Carolina in Asheville. He'll be talking to us about analyzing the performance of different parameter settings with ensemble nowcasting tropical cyclone precipitation. Once it loads. There we go. Awesome, take it away. Yep.
All right, so thank you for that introduction. I'll just get right into it. So as you all know, flash flood warnings are crucial for communication with the public about a weather hazard that's often dangerous and deadly. Longer lead times for these warnings allow for more preparation, leading to better overall protection of life and property. But unfortunately, over the last decade, the progress in increasing these lead times has slowed considerably. So to address this, a new precipitation nowcasting method based off the multi-radar multi-sensor network, MRMS, is being tested with the goal of increasing these lead times. These precipitation nowcasts are high resolution and short-term rain rate forecasts that are based heavily off of Lagrangian persistence, which means that an area precipitation is assumed to keep the same structure and shape and intensity as it's moved along an estimated advection field. Data for these nowcast data is incorporated from the MRMS system with 1 kilometer and 2-minute resolutions. And the reason why MRMS is such a good source to get data from for these is because MRMS combines data from existing radar data and a wide variety of other data sources, including lightning data, rain gauge data, and numerical weather prediction data to create a wide variety of precipitation and severe weather products. And the goal for these nowcasts, or any nowcast, is for the output to be as similar to reality or observations as possible. And another thing to note that's important is that this study focuses completely on tropical cyclones. It uses 2 case studies. The nowcasts were run using the short-term ensemble prediction system, or STEPS, which uses the Lucas-Canard optical flow method. And what the Lucas-Canard method does is it looks at image sequences. So in this case, for example, if I used a 20 UTC run, it would look at frames of precipitation from like 1956, 1958, and 2000 UTC, looking at how the different pixels, the different colored pixels move to make that estimation. And through that and some determination of relative uncertainties in small scale features and precipitation evolution, an ensemble of precipitation rates, of potential precipitation rates is generated. The step simulations were done using PySteps, which is open source Python package available to anyone in the public. And through inputting that MRMS instantaneous precipitation rate data, PySteps is able to produce 2-minute resolution time steps and a 60-minute nowcast forecast generation. Each simulation was done at the top of each hour chosen. And the nice thing about PySteps is it allows for a wide range of statistical analysis in determining whether your nowcast performed well or not so well compared to observations. The particular case studies chosen were Hurricanes Ian and Henri. And the reason why these were chosen was that the precipitation structures in these cases were significantly different. Ian's was characteristic of a strong tropical cyclone with a well-defined eye wall and large bands of very heavy precipitation, while Henri was much more disorganized as it was experiencing exotropical transition. It had a more frontal-based structure as it approached landfall. So comparing these two cases allowed for determination of whether different parameter values were needed for the best nowcast. And these here were the case parameters chosen for testing and the values. So every single possible combination was used for both tests, for both cases here. So I'll just define each of these right now. The minimum advection tracking rate is simply a threshold for the determination of the advection field. For example, if I chose 20 millimeters an hour for this, it would only analyze the movement of the pixels representing 20 millimeters an hour and above in that estimation. Number of ensemble members is pretty self-explanatory. It's a number of unique nowcasts in a complete ensemble set. And the seed value determines a randomization of small scale values through a pseudorandom through generating a pseudorandom set of numbers. And here is one example of how an ensemble mean output can change just by changing one parameter value. On the left, you have observed rates, and on the right, you have two examples of ensemble mean output. Both of them have the same number of ensemble members, 30 ensemble members, and the same seed value, 0. But as you change from 10 millimeters an hour advection threshold to 40, you can clearly see that performance is better, particularly with the area of heavy precipitation that becomes more closely aligned with observed rates. Although it's still a little bit too far to the west, it is clearly better than the one at the top. And another example, this time from Henri, with the same setup, the same number of ensemble members. Well, it's different from the last example, but both of the ensemble mean examples here are the same number, 10 ensemble members and 42 for a seed value. This time, 40 millimeters an hour has the worst performance, and as you change it to 0.5, it becomes more closely aligned with observed rates. For example, using the 40 millimeter an hour advection threshold, you miss almost all of the precipitation over Long Island and parts of central New Jersey. And there were a few specific performance statistic values that were used. I'll go ahead and define those three. Fraction skill score basically looks at the similarity of forecast and observed grids, looking at each of the individual cells, seeing if they're similar and that they both exceed or do not exceed a threshold rate, which was 1 millimeter an hour in this case. The relative operating characteristic curve gives probability of detection versus false alarm rates. And the area underneath that curve can be used to determine forecast skill because as probability of detection increases and false alarm rates decrease, that area under the curve increases. And finally, Pearson correlation coefficient simply tells you the correlation or relatedness of two things, in this case, forecast to observed rates. And here you have some results for Ian. You can see here performance differences as number of ensemble members change and seed value change. And if you look at this it's really hard to see any differences. That it really looks like they're all the same, but there are some subtle differences as these values are changed, especially in correlation coefficient. And those are more easily viewed using these line graphs that show the progression of correlation throughout the entire nowcast. You can see as you move from 10 ensemble members to 20, you increase correlation slightly. And again, as you move from 20 to 30. But after completing some t-tests for significance using 0.05 as the threshold for significance, those differences were found to not be significant. And also were the changes in seed parameter, the changes in correlation with changes in seed value, those changes were also found to not be significant. On the other hand, when advection tracking rate was changed, a wider spread of results was found. You can clearly see 40 millimeters an hour performed the best here. And differences between correlations from 40 millimeters an hour and all the others, 0.5, 10, and 20, were found to be strongly significant. And I'm going to go through all of those same types of results, this time for Henri. Again, it looks very similar to Ian's results. Very small, subtle changes as number of ensemble members change and seed value change. The only difference, which isn't shown here, is that the variation in the data leading to these averages is much smaller. So that allows for a difference like you see between 0 seed and 42 seed values to be found as strongly significant. However, the other differences are not found to be significant, along with all the differences for ensemble, number of ensemble members. But again, you can see as you move from 10 ensemble members to 20 ensemble members, you increase correlation, and then slightly again as you move to 30. And like Ian, less so than Ian, you have a less of a spread than Ian, but you still have a larger spread with changes in advection tracking, this time mainly because of the lower performance of 40 millimeters an hour. And one of the reasons why that may be the case is because of the lack of areas that are 40 millimeters an hour and greater in Henri. So what you're doing is you're looking at very small sections of the storm, the movement of very small portions of the storm to determine an overall advection field for the entire brain. You can see averaged performance differences by the hour for area under rock curve and fraction skill score. And you can see the fluctuations are fairly low for these. So it's pretty consistent with hour by hour performance values for these. So it shows a nice level of consistency. And the main summary and takeaways here is that although the study does not quantify a potential increase in flash flood lead time, unfortunately, there does seem to be a high potential for usefulness in increasing this lead time and increasing accuracy of flash flood warning prediction if the right parameter values are used and a lot more testing is done. And while advection tracking threshold seems to be the most important parameter to get right, that best value differs between these two tropical cyclone cases. Ian's best value is 40 millimeters an hour, while Henri's is 0.5. And while the number of ensemble members in seed value carry less significance, patterns do exist. 30 ensemble members tends to perform better. Also with seed value 42, a value of 42 tends to perform worse. And lastly, more research is needed for if this is going to be implemented operationally, if this nowcasting scheme will be. More case studies, a lot more case studies, parameter value combinations. There are really billions of parameter value combinations that could be done, and different thresholds for fraction skill score and area under rock curve. And that's all I have. Any questions? Do you have any questions? Oh. Okay. Sorry.
You mentioned why 40 millimeters per hour might have been worse performance for Henry, but why was 10 millimeters per hour worse performance for Eva?
You know what? Honestly, not completely sure. one of the reasons why, well, one of the reasons why 40 may have been better for Ian is because of how there was a well-defined eye wall. There was with those rates that were much higher, but I'm not really, I can't say I'm completely sure why 10 performed worse there. Yes.
If you were gonna use this operationally, do you foresee like basically having an infection tracking threshold that would vary depending on like
Definitely.
the type of PC or the
Definitely. Yeah, for sure.
Well, I'm gonna say thing, you could have this environmental and the health safety what the investment is, and maybe it could be dynamically varying and how it can be if the environment is supporting to that.
All right, well, now we can disperse for about a 15-minute break, or actually more like 17 minutes now. Yep. So see you guys at 3:30.
Get into it. So let's see this image here. We have to the left, we have the Atlantic Ocean, and to the right, we have Africa. And this is infrared imagery. And I want to ask you all a quick question. What do you all see first?
pretty colors.
So let's get into what that actually is. So what are African easterly waves and why should you care about them? Well, firstly, a majority of Atlantic tropical cyclones develop from African easterly waves. So with this diagram, there's three main features I want to bring to your attention. To the north, we have Saharan air layer, which is defined by dry air from the Sahara Desert. To the south, we have a lot of tropical thunderstorms, and in between, this blue arrow is showing the African easterly jet moving from east to west. And these little bumps in that jet is our African easterly waves. And sometimes these are synoptic waves at the period of around 3 to 4 days. So every 3 to 4 days, you'll see them come off the coast and occasionally develop into tropical cyclones as seen there. The main region of note here is the coastal region. This is where these waves are transitioning from continental to marine environment, which is very important. A lot of big changes going on. There's a lot of difficulties in forecasting. Like for example, this figure shows on the right, this is model output around 3 days out, rainfall in millimeters per hour, the European on top and the GFS on the bottom. And these are for the exact same wave, the exact same, just less than 3 days out, and their structures are almost completely different. Plus, in-situ observations in this region have been lacking in the past, which is problematic. And understanding this region and giving you more information is very critical. Downstream impacts from these storms can be very significant. For example, this wave actually did end up becoming Hurricane Ian, making landfall in Florida as a Category 4 about 2 weeks later. So NASA decides to do the Convective Process Experiment Cabo Verde, or CPEC-CV. It was really designed to patch up the lack of data in the Eastern Tropical Atlantic. So they carried it out based on Sal Island, which is just off the coast of West Africa in Cabo Verde Island chain, marked by that red marker on the map. Radiosondes were launched at least twice a day. Occasionally they launched a third. And flights also were sent out to get a bigger picture of the whole area, more data for the whole area. So how do African easterly waves influence offshore and coastal precipitation? So these are more infrared graphics showing convection, like thunderstorms. So those yellows and blues are convection, and that's associated with thunderstorms. These red arrows are showing like the wind direction, and the green star, a little hard to see, shows where Sal is. Northerlies, as we can see in the top image, will indicate a wave that's approaching. And the bottom image, there's a slight southerlies showing that a wave is exiting the region. So using this, we hypothesize that significant northerly winds at Sal will increase coastal precipitation due to enhanced onshore convergence. So this figure shows the meridional wind plotted from the radiosonde data from all 29 days that radiosondes were launched from Sal. The data goes from 1,000 hectopascals up to 300 hectopascals. on the y-axis and goes from the 1st of September to the 29th on the x-axis. This is just meridional wind. And we want to focus on the 600 hectopascal layer and below, which is just a little bit less than halfway up and down. And we can see the purple winds denote southerly winds, and the orange-brown shows northerly. And we have these pillars of orange, kind of like around the 7th-ish, between 5 and 10, after 10, then a really big one after 20. These are our approaching African easterly waves, so we can see. So we categorize each day based on a northerly or southerly day if the value of these winds exceeded half a standard deviation from the mean. And we had 9 northerly wind days and 7 southerly wind days. We also ended up using the integrated multi-satellite retrievals for GPM, or iMerge data, to see where the precipitation is occurring. So we can couple those together to see when the precipitation is occurring, where the African easterly wave is at the same time. So first results, these are 2 images showing, on the left we have our northerly days, a composite of all those days combined and averaged together. And on the right we have a composite rainfall of southerly days. This is in millimeters per day. We have our more heavier rainfall in the blues and darker blues, and lighter than the light greens. And we have more rainfall to the south in the intertropical convergence zone on northerly days on the left, and more rainfall on the coast during our southerly days on the right. Northerly days, we have more precipitation in the ITCZ zone, which is marked by that orange circle, orange oval. And we have northerly winds as seen by the diagram. The red arrow is right at Sal. We kind of assume that enhanced precipitation is likely due to the African easterly wave trough advecting that moisture northwards. And for our southerly days, we have more enhanced coastal precipitation marked by that red oval. That's more likely due to the next African easterly wave, not the one causing the southerly winds on Sal. As you can see to the left side of the right figure, the red arrow is pointing northwards, so we have a southerly wind on Sal, but that's more marked by the first African easterly wave, and the precipitation is much more closer to the second African easterly wave. So not that deep of a connection there. So now we have that timeline link established, we can talk about African easterly wave strength. Variability with African easterly waves is very high, and notably with precipitation. This figure shows 4 different days of African easterly waves. These are different waves, but they are roughly at the same location where this, the data has come from. And that's marked right by that red line. The trough is approximately at that red line for all 4 days. And the precipitation is very different for all 4 of them. So we want to find a relationship between the strength of the waves and precipitation totals, so maybe better get an idea of how each wave varies. So we hypothesized that stronger waves would bring more precipitation. So what we did was, to quantify that rainfall, we created 2 regions. We have the orange rectangle to the south, which is our ITCZ region, and the red rectangle to the east, which is our coastal region. You can kind of see the northerly precip, there's a lot more precipitation in that orange rectangle versus the right, we have a lot more in the red rectangle. So we also use the meridional wind speed again to kind of as a proxy for strength and how that's stronger and how that relates to that precipitation in the 2 regions. So plotted these in scatter plots. On the left, we have the coastal region relationship, and on the right, we have the ITCZ region relationship. Each dot represents 1 day. Each blue dot is 1 day. We have on the y-axis, that would be the daily rainfall in that region, and on the x-axis, that is the meridional wind. So the relationship is fairly weak, very a lot of spread. That red line is the line of best fit, and it kind of tries to get a linear relationship between these 2 factors. And the dots aren't really all directly on the line, so it's kind of a weaker relationship. But the tendencies are still there. In a coastal region, you have slightly more dots up to higher up in precipitation, and you have higher velocities, positive velocities So those would be our southerly winds. And on the ITZ region, our northerly winds, we have higher precipitation on our northerly wind days, which is our negative values to the left side, which does line up with our previous results. Southerly days, as previously mentioned, the figure before, is likely that's more associated with the next after east of the wave, not the one that is currently causing the wind on south. So that's probably a big reason why that relationship is so weak, because it's not even the same wave. So yeah, and for the ITCZ region relationship, that is associated with the current wave, not the next one. So that might be a good reason why that wave is a bit more correlated. And we see that relationship a little bit stronger, still not super closely related. So in conclusion, there was a pretty clear relationship between our direction of marine wind on south and location of strong precipitation. But there was a weaker relationship between the strength of the marine wind speed and the amount of precipitation, especially in that coastal region, which was the main objective. However, this study does really highlight the importance of forecasting the correct after each of the wave location. As we go back to our model output data, the European on top and the GFS on the bottom, once again, the European kind of shows more rain in the coastal area and the GFS closer far south into the ITC region. So there's a decent chance that the main difference between these two models is just simply the location of the wave other than anything else. And that's all I have. Thank you. Any questions? Corey?
What future research could be done?
Well, I think there's a lot of things that could be done. I think a larger time scale for one, having more waves, more years, et cetera, because it's just 1 month. But it is still hard to get that observational data from out there. I would say we were short on time. We wanted to use curvature persistence data that we had for these afternoon waves for strength, but we didn't really have time to get into that all the way. So that would be something that people could look into in the future as well.
So you mentioned that they think the waves that became healing. Did you look at what was different about that one in this form and the other waves did not?
Well, that was like one of the things we talked about, especially early on, was like how that happened. But that Ian developed so far down the line, it was like all the way into the Caribbean where that developed. We did have a wave develop in our region that was Hermine developed, and that wave was the one way early on when it's very clear the northerlies, but that one was also an anomaly because it cut north very early and didn't really go through the region. So, but yeah, if it was, that's all in the region people could like further research into is use more data from like further west and see how that relates to development as well.
That would be a question.
Get started with the next talk here. It will be Jayla Lamar. She's a sophomore studying atmospheric sciences at the University of Georgia. She'll be talking to us about public characterization of tornado risks. Gonna take a few moments apparently. All right. Go ahead.
Thank you. Good evening, everyone. I'm going to get right into the background of my project. Now, the Storm Prediction Center, also known as the SPC, issues a convective outlook that highlights the threat of tornadoes, convective wind, and hail all across the United States. The outlook currently prioritizes probability information. However, though, in recent years, SPC has been considering adding new information about the intensity of these hazards. So, before they can make this addition, we would need to understand how do members of the public weigh probability versus intensity information? Does this information actually matter to the people? Now, there have been multiple studies that have been conducted on the convective outlook, focusing on how members of the public interpret categorical words used to convey risk, such as what is a slight risk, what is a moderate risk, and what is a high risk. However, there is relatively very little research done on what risk really means to a person. For example, if a high risk was issued, if a high risk was issued for a tornado tomorrow evening, would that mean that there's a low probability of the storm that will be high in intensity? Or would that mean that there's going to be a high probability of a storm that will be low in intensity? Now, that question leads us straight into our study. The data for the study was derived straight from the Extreme Weather in Society Survey, which is a yearly online survey administered by the University of Oklahoma to U.S. adults ages 18 and up. We specifically focus on responses from the 2017 survey and from the 2019 survey. Our methods include a combination of both quantitative and qualitative analysis of the survey responses, which we evaluate using R. We focus primarily on just 3 survey questions that I will be going into detail on in the following slides. Now, diving into the first survey question. When thinking about the risk of tornadoes, is probability more important than intensity, or is intensity more important than probability? We go ahead and we allow the participants to answer which set of information they believe is more important to them. What the first answer choice would be probability is much more important than intensity, and the last being intensity is much more important than probability. If not these 2 extremes, does this person's opinion lie somewhere in between? Taking all those results, we are able to display our results using a box plot. And as you can see, a majority of participants had chose that probability and intensity are equally important to consider when thinking about a tornado risk. You can also see that there is a little slight lean towards more intensity information than probability information. However, taking these results, we asked ourselves, are there any other factors that may affect the way which information a person may choose when thinking about a tornado risk, such as education level? Would this affect the person's comprehension of that risk, or their experience of the tornadoes, or their exposure to tornadoes? If a person were to experience more tornadoes, would this affect the information that they lean towards or the information they rely on? Well, we decided to go ahead and take these questions and put them into subgroup analysis. Now, the first analysis, I'm just going to break this down a little bit. We took those results and we broke them down into 2 categories. Now, our responses were split into 2 groups, with those that had less than a bachelor's degree and those that had more than a bachelor's degree or more. As you can see, there's a very slight, almost very little variation in distribution. Most respondents still chose that probability and intensity are equally important despite differences in education levels. Next, moving on to tornado exposure, we decided to split it down into 3 categories. One being infrequent tornadoes, meaning that person experiences a low amount of tornadoes in a year, such as someone that lives in Alaska. They don't see tornadoes very often. And 2, average tornadoes, they see just an average number of tornadoes based on their location. For example, that would be someone that lives along the East Coast. A real world example right now would probably be Tennessee, who's seeing some tornadoes right now. That's just an average amount. Or, and the last group would be 3, those that experience frequent tornadoes, such as someone that lives here in Oklahoma. As you can see as well, the distribution is very closely related to the 2 previous plots, where most people had chosen probability and intensity are equally important to each other, despite their exposure to it and despite their education level. Moving on into our second survey question, we decided to take a more qualitative approach. And we asked the participant, what does it mean if there is a blank of tornadoes in your area tomorrow evening? Now, this blank was then filled in with a randomized risk word. So either that person received that they got a slight risk in their location, a moderate risk in their location, or high risk in their location. Then that participant was prompted to provide a sentence or 2 interpreting what that phrase meant to them. Now, I went ahead and I went through all these survey responses. There was about 3,000 of them that I had to go through. And I determined, is that person's response more influenced by probability, severity, both sets of information, or something else? We used a bar plot once again, and as you see along the x-axis, we have each category that response may have fallen into, and the percentage of respondents responses that may have fallen into that category. As you see, 60% of survey respondents had used probabilities to interpret that given categorical risk, rather than 7% who chose severity to describe it, and 3% only chose both to describe it. When we broke this down by education, we see the same distribution. 56% of those that had less than a bachelor's degree chose probability to explain what that risk meant to them, and 64% chose probability to explain what the risk meant to them. Then breaking it down by tornado exposure, once again, we see the same distribution. There was not much variation in it. We move on now to our next survey question, where we took a reverse of the previous survey question. So instead of giving that person a risk category for them to interpret, we instead gave them a probability and an intensity level, which they were then allowed to choose which risk category they believe best described that set of information they were given. In this question, it states that a 1% chance of a severe EF3 tornado may be less risky than a 10% chance of a moderate EF2 tornado, or a 2% chance of a devastating EF4 tornado may be more risky than a 90% chance of a light EFO tornado. We would like to know how you, the participant, weigh the probability and intensity of extreme weather events. This participant was then allowed to rate the risk of the following tornado scenario. The scenario states a blank chance of blank tornado. That blank was then filled in with a randomized probability and a randomized intensity level, and the participant was then allowed to go in and choose which risk level they believe best fit that scenario. I am extremely sorry that this presentation is cutting off. The rest of it is really weird. It wasn't formatted like that, but we'll just move on to the plots. We decided to use a linear regression model to display that relationship. As you can see, I'm going to explain over here how exactly we observed this relationship. Over to our left is our probability plot, which plots the difference between probability and risk. We have along the x-axis a minimum of a 0% chance of a tornado occurring and 100% chance of a tornado occurring. And then we have our risk levels listed along the y-axis. Then for our intensity, we have intensity levels taken from the enhanced Fujita scale, also known as the EF scale, going from an EF0 level tornado, which is less devastating, less intense, all the way up to an EF5 tornado, which is more devastating and more intense. As you can see, just taking an overall picture of it, an overall look of it, there was a positive relationship between the information given and the risk level that the participant chose. This means that there's an increase, that as there's an increase in probability value or intensity level, this also increases one's risk perception. But if we take an even closer look just at our probability versus risk, we see that there is a steeper line of slope. This signifies that probability has a much stronger impact on one's risk perception than intensity. Then breaking this down by education, we see the same pattern once again. Despite differences in education level, there's still a positive relationship between the information given and the level of risk that person discerns from that information given. And again, as we see in our responses by the tornado exposure, there is still a positive relationship between the information that's given, increase of the information given, and the increase in risk level. Now, taking all of our results together, using our quantitative analysis, we were able to conclude that people weigh probability and intensity equally important to each other, and both of them are used to discern risk. In our qualitative data, using our second survey question, we see that probability may come to mind a lot more frequently than intensity information. However, this does not diminish the importance of intensity information overall. Still, a majority of the public use both probability and intensity information equally when discerning risk. Using those conclusions, we suggest that the SBC should include more explicit intensity information to enhance their efficiency of the convective outlook overall. We suggest that future research should be conducted on subgroup analysis, for example, what is the difference between the risk perception of someone that lives in Oklahoma, who sees tornadoes a lot more frequently, to someone that lives out in like California? Secondly, we suggest that more realistic studies should be conducted on those that have survived hurricanes or have witnessed, not hurricanes, sorry, tornadoes, or have witnessed tornadoes, because someone might respond a little bit differently in a hypothetical scenario rather than a realistic scenario. We believe that both these studies will give us a lot more insight on how the public behaves during a severe weather outbreak. And we believe that this information will help us improve weather communication using the convective outlook for non-professionals and professional users alike. Thank you so much for your time. Are there any questions?
This is your personal opinion. Do you think including like the color scheme may change the results
Color scheme.
as far as indicating like the severity of?
Yes, that does make some sort of difference. And more so like some of the literature review, some of the background information that I did. When it comes to the convective outlook and their use of colors and like risk words, that does have an effect on people's response and perception, but it can be quite confusing right now, or at least the outlook that we have right now, which they're doing more research on right now, honestly. That's
So a similar kind of question, was there any considerations, because they do these tornado risks, and there's only like, 5 different categories you can go into. Would there be any, do you think maybe like 5 categories from like marginal to high risk? Is that too many categories? Or do you think it can be a little more specific, or do you think we need to like dive back a little bit?
That's a very interesting question. I will say they did have a smaller number of risk categories a few years back, right? And then they decided to add a couple more to make it more clear to people, to make it easier to understand. But in my personal opinion, I feel like without explanation of those new terms that they use, those added terms, it's not really going to help people's comprehension as much as they thought it would, because they just added a few extra terms of like, okay, there it goes, just understand what it means, without explaining exactly what they mean or what kind of probability lies in it or what kind of intensity that describes.
Yeah, and another thing is like, even they have, sometimes they don't, but sometimes they put those hashes, those hash markers to be like significant severe.
Mhm.
I mean, I didn't even know what that meant for the longest time. I was
To
like,
tell you the truth, I didn't either.
I was like, ooh, there's a line.
Exactly.
I had no idea what it meant. Of course, now I know now, but do you think that's like kind of confusing?
I do believe it can be quite confusing. I feel like more explanation should be put into it before they put it out.
I was wondering what were some sort of responses that fell into something else category that you identified?
Now I got a few very interesting responses in that survey. I will say, for example, one that I can remember right now, someone put, when they got a high risk category, they put that means that the cows are flying. And I'm like, I'm not sure what that means. I don't know if that's severity. I don't know. So I just put it in something different,
I'm not sure what that is.
Yeah, pretty much. Any other questions? All right, thank you so much.
All right, so our last in-person talk for today be a bit shorter. Brina Lemke, who is a junior studying atmospheric and oceanic sciences and mathematics at the University of California, Los Angeles, and she'll be talking to us about storm displacement errors in the Warn-On forecast system. So go ahead and take it away.
Okay, so yeah, what he said. I thought these skills would help, but maybe not. Yeah, so just to get into it, All right, so I'm pretty sure most of you are hopefully familiar with the watch and the warning system, the public alerts that are released to the public in order to let people know in advance of when severe weather is happening, will happen, or could be happening. The watch generally has a 3-hour lead time, can be much more, can be much less. And then the warning usually only has a 30-minute lead time. And what tends to happen is that people often don't really take much notice of watches because they don't see it as to piggyback off of Jada's presentation. It feels like a low probability thing. So even if they're in that watch zone, and because they happen so often in some areas, they're much less likely to take action than they would in, say, a tornado warning. But at that point, they only have a 30-minute lead time on average, sometimes much less, sometimes a little bit more. But there are cases where people who stay in mobile homes or doctors and nurses working at hospitals need like 30 minutes minimum warning in order to fully prepare for impact. So the current lead time really isn't adequate for ensuring that everybody is aware and likely to act on that alert. So what we need to do is we need to fill the gap between the watch and the warning, something that is localized still, but also probabilistic, like high probability. So just getting the middle ground there where people don't necessarily have a tornado warning yet, but even as much as 90 minutes up to, as we'll see, 3 hours, knowing that they're in a smaller localized zone that is much more likely to see severe weather, hopefully will get people to take it more seriously than a watch. And that's where we get the warn on forecast system. So this is a rapidly updating probabilistic severe weather forecast system. It uses 36 data assimilation numbers. 18 of those are used for forecasts. And as you'll see, I also have a paintball plot. I love paintball plot. And each different color is a different ensemble member. So when you start seeing those areas that get darker, the gray, those are areas that are highly likely or more likely, as per the forecast, to have severe weather happening right there. And as the darker spots are observed storms. New forecasts are released every 30 minutes. They're spaced out in 5-minute intervals within each forecast, and they can provide 3 to 6 hours of lead time, although in theory, the ones that have a longer lead time are going to be less accurate because it's farther in the future. That's generally how forecasts work. But yeah, so even within this time frame, and also fun fact, this is from the storms that happened on the day that I got here, June 15th. And you'll notice that there are some errors in the storm locations. So the areas where there's where it gets darker gray is where the watch is going to say, hey, there's probably going to be a storm here, or this storm is probably going to move here, but it tends to be a bit off. So what we're looking to do is measure the storm displacement errors. Just taking the difference between centroid locations of each storms. Each storm is each storm is connected to a storm object that can be determined by intensity or updraft helicity. And what needs to happen is each of those storm objects that is predicted and each one that is observed need to be compared. And hopefully you get matches where the storms are pretty much in the same place, it's more accurate, but there's also false alarms where a storm is predicted but doesn't actually happen, and misses where a storm happens but the WAPs didn't predict it. And in order to match these storms, the WAPs we use a total interest score with this equation right here, which is just measuring distances between the centroid and the
boundary of the storm. And this gives you a score on a scale of 0 to 1. The closer it is to 1, the more likely those storms should be matched as a pair. And generally we use a threshold of 0.2. So anything that has a total interest score below 0.2 does not get considered a match within the storm. For my particular project, I just wanted to look at isolated cells. There are also QLCSs and other multicellular, just non-isolated systems that may propagate differently or be predicted differently. And there's also going to be more range in the length for the centroid to jump around a bit between different forecast times. So in order to sort that out, I used a method from Potvin et al. 2022. Unfortunately, I don't have solidity values, so I was not able to take that into account. But area, eccentricity, and length are all variables that I was able to use to hopefully sort out most of the non-isolated cell storms from my data. And yeah, so that's pretty much where I left off last time as well, but coming up with the results, gonna talk to my mentors about some stuff tomorrow. So I can't share exactly what I've found because, you know, but yeah, so there's a whole bunch of variables I've been looking at. Year, for example, has been interesting because there's only 4 years of data. So that's not a huge sample size, even though there's a ton of data within each year. And also the data assimilation method changed slightly between, or maybe completely, I think, actually between 2018 and 19. So the 2017 and 18 WAPS forecasts were based on a different method. And from what I've seen so far, it looks pretty much the same in terms of at least averages and average storm displacement errors. But it's hard to compare or to say that there is a clear difference there, just because it is such a small sample size. Other things I've been looking at have been storm age, because the younger a storm is, the less that storm's data has been assimilated into the WAPS, the longer a storm has been identified in the system and predicted in the system, the more data it has to predict its path moving forward. Lead time, the farther out you go, the less accurate it's probably going to be. So yeah, there's a lot of things I've been looking at. I've made a lot of many plots, which are very fun to look at, but I'm excited to see what we can find that might help out.
I guess I missed this, the last time you're doing your 5-minute presentation, but that's really cool that you were able to it was like you were able to use data from literally as the storms were coming in, as you were like, oh, first day, here's your storms. Storms we're looking at. Was that intentional? Like, were they like, or were they going to look at other storm data, but then they were like, ooh, look at this one we found.
Oh, I just chose that one to put up on the slides.
Oh.
That was just one of the 30-minute spaced forecasts that I just found interesting. All of the previous WAPS outputs from the big storm days, including June 15th, pretty sure it was June 15th, is all available online if you want to go and play around. There's paintball plots, you can turn on the observed storm locations. There's also, I go back to the beginning, actually, the probabilistic maps. So yeah, so instead of just being deterministic, this actually looks at how likely is each area going to get a storm in general. And it's pretty accurate, especially in the short run, but there are, like, if you look at the bottom left corner of the watch, there's a storm that was predicted there that didn't quite show up, but I don't know, maybe it was correlated to this one. Actually, there is a bit of light blue still over there in the middle one, but yeah. Still working on it, but it's much, I still think it's much better than sending out a watch and then having people panic when they suddenly get a warning and weren't paying attention to the weather. I mean, I don't know who doesn't pay attention to weather. fishing.
So what are your plans for the next 2 weeks? You're staying a little bit longer since you started later.
So I've started coming up with some results that I'm going to discuss with my mentors tomorrow, hopefully, or I think we're meeting on Monday, so I have a little more time to do more stuff. But yeah, I'm going to spend the next 2 weeks finishing up my paper. I have my full 12-minute talk next Friday, so come to that if you want to. And hopefully I'll have some interesting results to share.
Yeah. Okay, yep. All right. All right, so our last talk of the day will be virtual. Her name is Alexis Rodriguez. She's a junior studying atmospheric sciences at Western Kentucky University. She'll be talking to us about comparing severe weather communication, awareness, and response between non-Hispanic and Hispanic communities. All right, Alexis, you can take it away.
All right, thank you, Jonah. First of all, can everybody hear me?
Hold on 1 second. We're having some technical difficulties, but that's okay. We got plenty of time.
Sorry, Alexis. So
Yeah, give
we're
us a
gonna
few
change
seconds
the
here.
audio to the external speakers, so you'll be much louder.
Let's see, where is it at?
All right.
It's in the Zoom controls, actually.
Oh, it's in the Zoom control?
Come down here to the,
That.
and then switch it to the, yeah.
This one? Does that
Say
work?
something, Alexis.
Oh, can you hear me?
Yes,
Yes.
that's a lot better. Yes.
Okay.
All right.
Thank
Let me
you.
make
Sorry
this
about
full
that.
screen real quick. Where's the full screen button? There we go. Close that. Okay, you're good to go.
All right, thank you, Jonah. All right, so I gave my introduction, so I will just jump right in with a quick introduction of the purpose at hand. So, at my introduction, the Hispanic population are an important and growing group of the entire U.S. population. There's about a 20% increase of immigration of Hispanics come every year, according to the 2020 census, which results into the resources of severe weather preparation are only available in English, which causes inequities and inequalities in these communities whose primary language is Spanish. And this results in Hispanics are not as equally served than non-Hispanics because of cultural barriers. Cultural barriers would include language and cultural origin of where they come from. To emphasize on the purpose of severe weather hazard communication, we're giving a short background of a relevant hazard event. And my hazard event that I chose is the San Diego Cedar Fire of 2003. This fire consumed more than 280,000 acres and it caused 15 fatalities. About 27% of San Diego County's population were Latino, and 85% were monolingual or bilingual Spanish speakers. Unfortunately, all official information was in English and was then hastily translated to Spanish, which results in a rushed translation, which leads to a lack of important information to Hispanic communities. And thus, the government was criticized for failing to issue warnings at a proper time, did not lead these communities in the right direction on what protective actions to take. Other such events have also been studied, and my study will expand on which communication techniques are best to use before, during, and after a disaster event. So the data that I will be working with is the Severe Weather and Society Survey, the 2022 version, in both the English and Spanish versions. This is an annual nationwide survey, which the English version started in 2017 and the Spanish version began in 2021. The maps below the text are a geographic distribution of the number of participants from each region according to the National Weather Service standards. It cuts up into the Eastern region, the Southern region, the Central region, and the Western region. In the English version, there's about 1,400 participants. In the Spanish version, there's about 630 participants. And the methods that I will be working with for both of these surveys is the analyzing of questions of severe weather understanding and communication between English and Spanish speakers of the United States, and the usage of statistics, which will to analyze between Hispanics and non-Hispanics. And all analysis done with these surveys will be used in a computer application called the Statistical Package for Social Sciences, SPSS. So the following tables are the percentage of all the participants from both English and Spanish surveys. This is the percentage of participants are compared with the percentage of the total US population on the right-hand side of the tables. They also include demographic characteristics such as gender, age, ethnicity, race, and the NWS region that I mentioned previously. And my analysis will focus on the ethnicity demographic characteristic, which I have in the red rectangles on both the English and Spanish versions. So for my analysis, I will be focusing on 3 survey questions of interest. Question 1 is the understanding of the definitions between severe weather watches and warnings, if they understand their definitions. Question 2, how much they rely on certain sources of information. Do they rely on one specific information source? Do they rely less on one information source? And the third question of interest is the level of uncertainty of response to certain scenarios to issued warnings. Do they agree with a certain scenario? Do they not agree with a certain scenario? These questions I will analyze within SPSS. So my results in the first question of interest, about 47% of non-Hispanic respondents say they definitely know the difference between a tornado watch and a tornado warning, while 36% of Hispanic respondents say definitely yes. And there's about 38% of Hispanic respondents say probably yes, which will lead to half of the Hispanic participants approximately to know the difference between a watch and a warning, which is a hint that some of these Hispanics would be US born instead of foreign born, which will be a great difference to hint at. And that being said, about 19% of Hispanic respondents say they are unsure of the difference between a watch and a warning. Any Hispanic respondents say unsure or below would imply that they are foreign born. They do not have the familiarity with a watch or a warning. So the next part of the first question to analyze between non-Hispanics and Hispanics is their understanding of the definition of an actual tornado watch and a tornado warning. Overall, non-Hispanics would know the difference between the two. About 20% of Hispanics mistaken a tornado watch for a tornado warning, with the choice of wording of dialect maybe becoming an issue. They would see one word saying that that's a tornado watch instead of a tornado warning. They may mistake those two words together. The same can be said about warnings mistake for a watch, although it is partially lower than mistaken a watch for a warning. And a lot of the data from the participants from these two questions is missing due to no response to this actual question. So results in the second question is the reliability of weather information sources, which ones do they rely more on, which ones do they rely less on. And I used a method in SPSS called the comparison of mean values. If the mean values are higher, that would imply that respondents will rely more on that source of weather information than others. So non-Hispanics will rely more on weather radios, television programs, and text messages with about a 3.5 and a 3.75 mean range. On the other hand, Hispanics will rely more on television, text messages, and outdoor warning sirens with about a 3.55 to 3.75 mean value range. Overall, Hispanics have a higher mean on all weather sources because some of these weather sources have a Spanish language option that they can use for that specific information. So results for the third survey question is the mean value of response to issue tornado warnings when they are issued in their area. I also use a mean comparison of mean values for this one. Higher mean values mean they agree more on the uncertainty due to issued warnings. So when I analyze this, both non-Hispanic and Hispanics have a higher agreement level on uncertainty of timing of an issued tornado warning, about a 2.8 to 3.0 mean value range. The level of uncertainty will lean more towards Hispanics throughout all scenarios, which comes from the uncertainty. The higher levels come from uncertainty of area. If a issued warning is in their area or a different area, they don't really have an agreement. And what actions to take about a 2.75 range. Like they are not sure what to do when a warning is issued for their area. They do not know what actions to take. So another aspect that I did for the third question is based on their response to tornado warnings, based on their living region of which region they reside from. And the residing region is based on the geographic map I presented in the data method section earlier. So the highest uncertainty of agreement is still in the timing when a tornado warning is issued, beginning and end, about a 2.7 and 2.85 range for all of the regions. Overall, the southern, western, and eastern region participants all have higher means compared to respondents from the central region. And what I also found was kind of interesting was respondents from the western region do not know what to do during an issued warning, about a 2.8 me value range, because respondents from the western region are not very familiar with tornado warnings compared to other regions. So to wrap up my analysis, Hispanic participants that are represented from both surveys have low familiarity and higher risk perception to severe weather events. And based on the analysis that I showed earlier, the central region participants have higher level of response due to prior experiences. Two events that I found that are based on the central region participants would be the Lubbock County, Texas tornado, which occurred in 1970, and the Setagosa County, Texas tornado, which happened in 1980, I believe. So, and they're different, which results into different cultural backgrounds and barriers Hispanic immigrants face are very important factors since information is often confusing to understand. Based on their origin history of where they come from, their level of concern of severe weather is higher. And thus, it's important for Hispanic immigrants to have more knowledge about preparedness for severe weather when in the state of an issued warning. So just to conclude what I've presented, the Hispanic population will continue to grow as the years go by. So the efforts for effective weather communication will need to focus on this cultural and demographic diversity within this group. An effort currently in the makes is the evolution and advancements of technology, such as the creation of machine learning methods, which can be an asset for proper translation of severe weather situations for Hispanic communities. And future studies will have to be done to analyze this technology and to develop and to continue development of recommended techniques to help with communicating severe weather information efficiently for Hispanic communities. And that concludes my presentation, and if there are any questions.
Right, any questions from the in-person audience or online? I'll relay them to her. Yeah.
I think for your first question, you were looking at different stratification of comprehension for tornado watches versus tornado warnings. And I think you showed that non-Hispanic populations understood, they definitely understood it 47% of the time versus 38% of the time for Hispanic population. And I think you said 36% of the time people of Hispanic population probably understood them. And I was wondering if the difference for non-Hispanic and Hispanic is the same for those less sure categories.
That's a long one. Can we go to your question one? It was one of her results slides. It's like the results slide for question one on your survey.
Okay.
Yeah. Might be easier to see it.
Are you talking about this one?
Yes.
Yeah, that's the one. Mm-hmm.
Yes. Okay. You know what the percentage of non-Hispanic respondents said for probably yes and unsure? Is the difference the same across all of them, or is it more pronounced for definitely yes.
Yeah, that needs to be the question. Would you mind if you can repeat your question just one more time so that I can be clear of what you are asking?
You might want to come up if you want to. He said he could email it.
Oh, okay. I'm sorry.
It's okay. It is a long-winded question. It's a lot for me to remember.
Yeah.
We think we got one in chat real quick on the virtual one. Oh, virtually too. Yeah, restating it. It was a long question.
Yeah.
Yes.
Just looking at this graph again, so there is a difference between the Hispanic and non-Hispanic population, but I think it's concerning that the non-Hispanic population also, a lot of them don't know the difference between the watch and the warning, and how would we better communicate that to everyone?
So do you think there's a difference in what again? I'm sorry. This is difficult. There is up here. If you want to just come and ask her. Yeah.
That way it's easier.
Yeah.
So I was just saying that in this graph, although there is a difference between the Hispanic and the non-Hispanic population, there's also, it's kind of concerning that everyone is not understanding watch and warning between both populations. So how can we better communicate that to everyone?
So that is a analysis that is ongoing. So every year they come up with different techniques to have more efficient information for both non-Hispanic and Hispanic communities. So if there are like different techniques that can help with better communication, then they can use that to have communication more efficient for both populations. So it's an ongoing process.
I can go. Okay, sounds good.
Hi, Alexis. I had a question.
Yes, sir.
So in this study, you kind of focused a little bit more on like tornado watches and warnings. I was curious if there are other natural disasters that maybe they are thinking about implementing, like wildfires, earthquakes, something along those lines.
Oh yes. So my team is going to expand on the study. I think like next year they're going to be focusing more on like winter weather and I think maybe hurricanes perhaps. So this study has just started this year, so it will continue on throughout each year, which will focus on different natural hazards besides like thunderstorms and tornadoes. So yes, one of my mentors say they in our plans for next couple of years, tropical weather, winter weather, and fire weather are in their plans.
We're good. All right, let's thank our speakers again.
Okay, so this was just day one of two in our sessions for the final talks. So thank you all for joining today. If you're in person or online, please grab some snacks in the back of the room, and we will meet here again. We'll get going at 9:25 a.m. tomorrow morning. All right, thank you so much.
Alrighty, I'm gonna get things set up for you guys here. And well, that gets up here. I would like to introduce our first speaker. We have Latoya Wilcoxon. She's a junior from Applied Meteorology, and she comes to us from Emory-Riddle Aeronautical University from the Prescott campus. So I'll get this up and running for you. Make sure that's working perfect.
Good morning. I'm very thankful to be here today. We like to have a small joke saying it's a not so safe space, but it's awesome to be able to present to you guys today. Before I can continue my presentation, I must give homage to those who have allowed me to be here today. So I'd like to thank the National Science Foundation grant for giving me the ability to have a paycheck while being here and funding my research. For Alex Marmol and Daphne Ledoux for admitting me into this research program. I would not be here if it would not be you guys. Amanda Kiss for my programming and my writing, and most importantly, my mentor, Brad Ilson, who has been my rock throughout this entire process. I'm sure we've all had those moments where you stare at a screen for days or hours and you'd have no leads. And I would do the walk of shame to his office and he would have every answer for me. So I'm very thankful for him. When it comes down to temperatures and your thermistor equipment, I feel like this is applicable to most of us today. You're going to choose a site, whether it be urban, country, or in a remote location. But with these thermistor sensors, they're not just going to be placed outside with no kind of shielding. So we have a solar radiation shield that will provide that coverage. Here we have 5 different models going from our Apogee, Barani, and Norman aspirated, our Barani unaspirated, and our Norman unaspirated. An aspirated solar radiation shield is a shield that has a small power source that creates mechanical ventilation within the inner core whenever there isn't any kind of low wind speed. An unaspirated solar radiation shield requires natural aspiration from winds. And one big thing to note here is that we're comparing these 4 models to the original data. So the Norman unaspirated, which is a 10-plate radiation shield, is the oldest model that we have. The other 4 that you see will be compared against this model for the duration of this research. The purpose is to compare newer aspirated and unaspirated radiation shield temperature measurements to Norman's original unaspirated radiation shield temperature data. Just to note that these are all going to be comparisons and differences. This is not to say that this sensor is better than the other, or this radiation shield is better than the other, or that these temperatures are true. These are all just comparisons and differences that we are finding today. The data that's been gathered has been 5 years in accumulation, 5-minute data with the aspirated and unaspirated temperature, solar radiation, wind speed, and relative humidity. We have a site over at OU North Campus, 2 sites about 100 meters in separation. The Norman site contains our unaspirated and aspirated Norman original data. And then we have the next 5 that contains our Apogee and our Barani models. To go into the variables that we're going to be considering, so temperature difference versus the wind speed. Temperature difference is that a Norman original data subtracted from the newer models, and we have our y-axis as that temperature difference, x-axis at the wind speed, and 2 meters. We divided our wind speed up into 3 different sections, being light, moderate to high. We had the statistical analysis for each of those being the mean and the root mean squared. What this means is we have the 0 line, and how you can read this chart is the data, the closer it is to that 0 line, the more these 2 different radiation shield temperature measurements are in agreement, right? So the further spread, the more that they're not getting the exact same temperature measurement. The root mean squared shows the difference in the temperatures being compared. The mean takes into correlation the positives and the negatives. So here we see for the light wind, we have a big spread going throughout all models, which is what we expect. That Norman original data does not have a mechanical aspirator, so it requires the natural ventilation of the wind speed. As that wind speed increases, so we see from 2 to 9 meters per second squared, we start to see these numbers start to become into more alignment. And anything with a greater wind speed, we see they're just basically right on top of each other, which is to be expected because now that natural ventilation is starting to pick up and is acting the same way that an aspirated radiation shield will be. We have the relative humidity for the x-axis, temperature difference for the y. We don't have anything significant to show with this. So relative humidity can be correlated to low wind speeds, but low wind speeds cannot necessarily be correlated to high relative humidity. And for this, it's not showing that even though there's more saturation in the air, that's having any effect on the aspirated fans. Solar radiation for the x-axis, temperature difference for the y-axis. We have this divided into the low, moderate, and high. The big piece here is that low solar radiation that we have broken up is our lower sun angles. So that covers our morning and our evening. And one thing to note with these solar radiation shields is that they're built to protect mainly against the high solar radiation angles. So the higher the sun is beaming down on our solar radiation shields, it's able to reflect that sun. But with that 10 plate stacked model for the morning and the evenings, as the sun rises, is able to peek into the side of that model. And that's where we can get a lot of extra radiative heating. What's interesting to note is that the brawny aspirated and the brawny unaspirated has a helical shape that's built for this kind of reflection. So they've taken into consideration these lower angles, and what we see is that they're doing what they're supposed to be doing as far as the reflection. One also thing to note is if you see these points more above this red line, that represents the Norman original data being warmer, and if the points are below the red line, that is the newer radiation shields being warmer, which once again is to be expected because that radiation shield does not have the mechanical aspiration. We also took into account how seasonal effects on temperature measurements. Here I have the x-axis broken down into winter, December to February, spring, March to May, summer, June to August, and fall, September to November, with the y-axis being the difference. The reason that you see three subplots is because the brawny aspirated was installed at the beginning of the year, and there's not enough data to give you enough significant findings throughout all 4 seasons because it hasn't been installed long enough. When you look at this graph, the first thing that you'll notice is pretty consistent. It's kind of hard to see the light blue, just in consideration, but they're pretty consistent throughout. If you want to look at it vertical to horizontal, looking for the winter, spring, and summer on the horizontal axis, they look pretty consistent throughout each model, which is what we want. We want to be able to see that these radiation shields are acting efficiently in the spring as well as the fall and summer, that there isn't a big difference. If we were to see that, then we know that we have a more of an issue that we have to look into as to why this radiation shield is giving us better temperatures in the winter compared to the summer. They all fall within their marginal range of their mechanical error from the manufacturer. And the big piece to take away here is that they're basically consistent throughout each with every model, even though they have like their own disparities. The significant findings is that the temperature difference is consistent throughout the seasons, which is what we expected. This is what we want to see out of our solar radiation shields. The temperature differences decrease as wind speed increases, which makes sense because as the natural ventilation increases with the wind speed, and there is no real impact with relative humidity. Even though the air is saturated, that has not been giving a bigger effect towards the temperature difference. And that's really what we're trying to find. And also, I'm not sponsored by Brawny, but the helical shape of the Brawny aspirators has been doing a great job as far as blocking out those lower solar radiation angles. The big piece to account for and why this research is so important is because as we continue to progress our research and we choose these different remote locations, we have these comparisons to see, is it beneficial for us to invest more money in these aspirated devices? We go from our original 10 plate shield, and now we're comparing it to our newest Brawny aspirated measurements, and they're basically aligning up. But we do have to take into account that our Brawny aspirated is the newest model. It does not have as much data, but for what has been recorded so far, the original plate and the newest model have been having some aligned temperature differences. So this is what we take into consideration throughout this research. Any questions? Yes. Go ahead.
Did you notice any negative effects from the newest model?
The Brawny? Not so much. We can go back towards our, basically for everything, and it's doing exactly what it's supposed to do. So we have the mean, if we even look at the root mean squared for the wind, it's only a 0.2 compared to our norm and aspirated. Looks pretty much in line, but they're right next to each other. The only issues I've had out of any sensor has been the apogee aspirated, and we've had to remove data for 4 days to account for a sensor error. As far as how the brawny aspirated and unaspirated, they've been perfect throughout each of these models.
So if you're putting in like a new Mesonet site in an area that didn't have like strong links, that have a lot of usage, would you, based on your results, you say that an aspirated sector, or is it not that simple?
I would say it really depends on your finances and your budget, because aspirated devices do require more maintenance. They also require power grid. And if it is low winds and we're trying to get accurate measurements, then maybe an aspirated would be the best bet. But also one thing that's cool about the brawny helical devices is that they like to, they promote that their helical design is just as efficient as an aspirated model would be. So I see manufacturers taking into account the cost. And if I were to, I'm going with the newest and improved with the brawny aspirated. That's just my personal opinion. But I really believe it's based off your budget and what you're trying to get out of your sources. Thank you.
I'm gonna reshare the screen here. Alex, did you do the full screen when you shared initially? Okay, I'm gonna try pulling up the next presentation and then just sharing the presentation and seeing if that helps. We were able to see the presentation, just had like a weird view of it, but everything else looks fine. You did great. No, you're fine. Okay, let's get the next one up. Sarah. There we go. Should be. Okay. Okay. So let's. We'll do this. Slideshow mode. Is it good? Okay, perfect. Okay, sorry about that. Our next speaker is going to be Sarah Henry, and I just realized for Latoya, I didn't say her title of her talk. I'm sorry. I'll remember to do that for future speakers. But Sarah comes to us as a junior from aerospace engineering, and she comes, excuse me, she's a major in aerospace engineering and comes to us from Illinois, from the University of Illinois at Urbana-Champaign. Her title of her talk is going to be Compound Heat Wave and Air Pollution Episodes in the Urban Environment. So take it away, Sarah.
Thank you. Heat waves and air pollution episodes are both events that affect the livelihood of people. I'm sure everybody here has seen the headlines recently, such as heat waves in the South and Southwest and the air pollution episodes in the Midwest and the New York State. A heat wave is a period of extreme heat lasting for several days, and they're becoming more frequent, more intense, and longer lasting due to climate change. An air pollution episode is when air quality exceeds the recommended levels, and increasing wildfire activity in the Western United States and Canada is increasing the hazards for these air pollution episodes. Furthermore, heat waves strain power grids, and a reliance on fossil fuels can increase further pollution. The goal of this study is to analyze and understand compound heat wave and air pollution episodes where extreme heat is coupled with elevated air pollution levels. To understand this, we need to understand the urban heat island and particulate matter less than 2.5 micrometers in diameter, or PM2.5. The UHI is a phenomenon where surface temperatures and air temperatures are elevated in urban areas relative to their surrounding rural environments. This is due to a lack of vegetation and concrete and road structures in the urban environment. The UHI has a synergistic relationship with heat waves, meaning they build up on each other. This can cause Death Island, where mortality is greater in urban areas during a heat wave. It also lengthens heat waves and has its greatest impact at night when there's little relief from the heat. PM 2.5 comes from the combustion of gases, oils, fuels, and wood, and has impacts on respiratory and cardiovascular diseases and can cause death. There are generally elevated levels in the urban environment due to industrial and traffic activity. I use two main data sets for this project. I use a daily minimum temperature, or TMIN, data set and a daily PM 2.5 concentration data set. Both of these are 1 kilometer grid resolution, which can capture the urban heat island effect and other small scale processes. To analyze urban areas, I use city shapefile data from the 2010 US Census Bureau, and this identifies 481 urban areas with a population greater than 50,000 people in the contiguous United States, or CONUS. I group these into 9 climate regions from the NOAA US climate regions. For each urban area, or UA, I define a surrounding rural area, or RA, and a surrounding background area, or BA. You can see in this figure up here, the urban area is in the center, the rural area is the second ring, and the background area is the third ring. For my study, I look across the entire CONUS with the 481 urban areas from May to September from 2003 to 2016. I define a heat wave as 3 days or more of TMIN exceeding a 90th percentile TMIN threshold as defined by the BA. I define an air pollution episode as 1 day or more of PM 2.5 concentrations exceeding 15 micrograms per cubic meter, which is the World Health Organization's 24-hour air quality guideline. I define a compound event, or CE, as 1 or more days within a heat wave when PM 2.5 concentrations exceed that 15 micrograms per cubic meter. I measure frequency by the number of occurrences of these events. I measure heat intensity as the difference between the measured TMIN and the 90th percentile TMIN. I measure pollution intensity as the difference between the PM 2.5 concentration and 15 micrograms per cubic meter. And I measure duration by the number of days in an event. First, I'm going to present my results on the heat wave analysis. Overall, it was found that the CONUS average frequency and duration were greater in the UA than the RA. The most frequent, intense, and longest lasting heat waves were in the Southwest and West regions. And the UHI impact can be seen on the frequency and duration of the heat waves, but not in the intensity. Comparing the urban to the rural areas, it was found that 99% of frequencies, 67% of intensities, and 96% of durations were greater in the UA than in the RA. Some notable outliers are Bakersfield, California, where the UA frequency was 212% greater than RA frequency, Hilton Head, South Carolina, where the UA frequency was 144% greater than the RA frequency, and Santa Cruz, California, where the UA frequency was 25% less than the RA frequency. Once again, it was found that the synergistic effect of the UHI on heat waves can be seen in the frequency and duration, but not in the intensity. And most urban environments were found to be more susceptible to heat waves than urban environments. Next, I present my air pollution episode analysis. Overall, it was found that the CONUS average frequency, intensity, and duration were all similar between the urban and rural areas. The most frequent and longest lasting air pollution episodes were in the Ohio Valley, Southeast, and Northeast regions, while the most intense air pollution episodes were in the Northern Rockies and Plains and Upper Midwest regions. Once again, comparing the urban to rural areas, it was found that 79% of frequencies, 59% of intensities, and 72% of durations were greater in the UA than in the RA. Some notable outliers are Bremerton, Washington, where the frequency was 650% greater in the UA than RA, and the duration was 253% greater in the UA than in the RA. Santa Barbara, California, where the frequency was 570% greater in the UA than the RA, and the San Francisco, Oakland, California area, where the intensity was 670% greater in the UA than in the RA. Overall, it was found that many urban environments are more susceptible to air pollution episodes than their surrounding rural environments. And it is also important to note that the regions that had the most air pollution episodes were the Ohio Southeast and Northeast regions, but those areas had similar events between the urban and rural areas. Finally, I have my CE or compound event analysis. And overall, it was found that the CONUS average frequency and heat intensity were greater in the UA than in the RA, but the pollution intensity and the duration were similar between the UA and RA. The most frequent, most pollution intense, and longest lasting CEs were found in the Ohio Valley, Southeast and Northeast regions, while the most heat intense CEs were found in the Southwest region, the West and Southwest regions. Comparing the urban to rural areas one last time, it was found that 91% of frequencies, 98% of heat intensities, 77% of pollution intensities, and 57% of durations were greater in the urban than in the rural areas. Some notable outliers are Seattle, Washington, where frequency was 1000% greater in the UA than RA. This was because there were 11 observed compound events in the urban area, while only 1 in the surrounding area. San Jose, California, where the frequency was 800% greater in the UA than RA. Bremerton, Washington, where the air pollution intensity was 470% greater in the UA than in the RA. And Santa Fe, New Mexico, where there were no compound events in either the UA or RA. Overall, it was found that the Ohio Valley, Southeast, and Northeast regions saw the most frequent, most intense in pollution, and longest CEs. This is likely due to those specific regions having frequent and long-lasting air pollution episodes as compared to heat wave events, while the West and Southwest regions saw the most intense in heat CE, which is conversely due to a result of frequent, intense, and long-lasting heat waves. This means that most urban areas were more susceptible to frequent, intense in heat and intense in pollution compound events than rural areas. To summarize, most urban environments are more susceptible to heat waves, air pollution episodes, and compound events than their surrounding rural environments. The synergistic effect of the UHI on heat waves was observed in the frequency and duration of a heat wave, but not in the intensity. The compound events are more intense in pollution in regions that have more air pollution episodes, and CEs are more intense in heat in regions that have more heat waves. Regions with the most air pollution episodes had similar events between the urban and rural areas. And future work will continue to analyze outlier cities to understand the mechanisms that control these events, such as the background climate of these regions. Specifically, where a city is surrounded by mountains, the urban area will tend to have either more heat waves or more air pollution episodes due to that environment being stuck in the city when it can't pass through that mountain. Thank you. It was 2003 to 2016.
Okay. Did you look at anything temporally to see if these were getting worse or better with like some of the changes in air pollution and all that?
We did, yes. We did some preliminary trend analysis, and overall there was a general positive trend for heat waves and general negative trend for air pollution episodes. And most likely for heat waves, that's due to climate change, but for air pollution episodes, that is due to local legislation on these pollutants. But it is important to note that these data sets are derived from other products, so it is not necessarily recommended to do trend analysis on these data that are sourced from things such as models and other things.
Are there any cases that you're studying that surprised you?
Yes, I think the Santa Fe, New Mexico, that was very interesting, because that area did have both frequent heat waves and some air pollution episodes. So it's interesting to see that none of them coincided with each other to create a compound event.
It seemed like Washington State kept popping out as like an outlier of cities in there.
Yeah.
Is there's something that's unique about the meteorology or maybe the topography as you suggested, like Seattle or Bremerton?
I think it does have to do with the background climate of that area, and the mountainous regions that surround it, as the incoming sea breeze gets blocked off by the mountains, so that some of that air can get stuck in the cities, or it can be quickly blown away.
Okay. I thought it was surprising because I figured like Washington State might have like more strict pollution regulations.
Yeah. Yeah, and wildfires being in western US, such as California, just south of there, that can transport those the pollutants up to there. Mhm.
What was your definition of like an urban area?
Yes, so an urban area was defined from the 2010 US Census, and they're regions that are greater than 50,000 people in population.
Okay.
Mhm.
That's it. Would you like to speak it one more time?
Thank you.
There we go. I was like, hold on.
It's an old computer.
Okay, I'll click 4 times instead of 2. Okay. So what I'm gonna do, let's do the same thing we did last time. I think that works. Yeah. Oh. Now it's, well, goodness gracious. So it's showing the presentation or presenter mode here. Slides here, and then online it's showing. Oh, well, would you want me to stop sharing and try again? Okay. No, that is fine. Let's. Oh, goodness gracious. Okay.
This one is.
No.
It's 2.
Oh, hold on. Let me try that one.
Yeah, that's.
Yeah, okay. See, we figured it out eventually.
Technology.
Okay. I'm gonna see if we can get. Right. There we go. Okay. Things should be good now. Sorry about that. You think after years of working with Zoom, we have it figured out? No. No. Okay, our next speaker is Brett Castro. He's a junior in atmospheric science, and he comes to us from the University of Albany, SUNY. And the presentation of Brett's title is Comparing Real-Time Convective Allowing Ensemble Forecasts Produced During 2021 and 2022 HWT Using Neighborhood and Surrogate Verification Methods. So, Brett, take it away.
Keep making people read my really long title.
It's okay.
Okay. How do I, oh, I have to actually click it. Or no?
Shoot the right arrow.
Oh, there it goes. Okay. All right. So I'm just going to do a quick rundown on CAMs or convective allowing models first. So recently, numerous high resolution convective allowing models or CAMs have become operational. And unlike your typical global models, which have coarser grid resolutions, are usually focus more on synoptic scale over medium time ranges,
These produce detailed short-range forecasts involving development and evolution of convection over much shorter time periods. They usually have grid resolutions of less than or equal to 4 kilometers. And not only can they actually resolve convection, but they can actually identify storm modes and specific threats in the model. So here's just an example of a simulation from June 16th it was actually just last month, her run, and it placed some of these supercells actually relatively well to what actually happened. So until very recently, until 2017 specifically, CAMs have been limited to deterministic models. And with the invention, there was the high resolution ensemble forecast system that was invented in 2017, which is actually an ensemble system for CAMs. So this consisted of 10 ensembles with varying model cores in physics. And it's actually has quite a good record. One of the issues, though, is going to the future, it's not really efficient to upgrade and maintain this system because it has different model cores and different physics regimes. So that kind of brings us to the motivation of our study here, which is we want to continue to further improve and streamline CAMs to increase the accuracy of short-range forecasting. And one of the ways that to make that a little bit more efficient is there's this concept of the Unified Forecast System, or UFS, which is basically meant to combine all these models into a single system, with the Rapid Refresh Forecast System, or RRFS, being the CAM implementation of that. And they're using a model core in that called the FE3 LAM, which is the Finite Volume Cube Limited Area Model. One of the issues, though, is we don't know too much about how this model performs at convective line resolutions. So to work on that, OU Map Lab during the 2021-2022 hazardous weather testbed ran an RRFS-like ensemble of 10 different ensembles. They initialized it each day, May through June, in both 2021 and 2022. And we would basically want to do is we took 10 cases from each of those years, and we want to compare the 2 years to see if there's any improvement between the 2 years, where improvement occurred, and so on. So we're going to be using a couple different verification methods for this. First is the standard neighborhood method, which is used to which we're going to be using to measure the accuracy of precipitation and observed reflectivity in the model compared to what was observed. And the other is the severe surrogate method, which basically uses helicity tracks as stand-in storm reports, and we're going to compare those to actual storm reports that were taken on that day. So just a quick breakdown of the standard neighborhood method. So one of the issues with CAMs is because they have such small grid resolutions, even a subtle displacement in convection in the CAM compared to real life is going to show up in a completely different grid. So if you're only doing, like, say, a binary probability at each grid, that's going to be a terrible, you're not going to be able, that's not going to be a good verification. So basically what we want to do is we want to take each individual grid and you pick some sort of predefined radius and draw around that grid. So you're going to encompass a certain amount of additional grid points and create this neighborhood. So that way you don't actually have to have the exact same grid points overlapping, as long as you have a similar amount of grid points that hit a certain threshold, let's say in reflectivity or precipitation in the model and in real life. That's a relatively good neighborhood probability. So you can see here that even though the exact same grid points aren't highlighted, you actually have, this is actually the same neighborhood probability applied to the central grid point in both observations and model forecasts. So because we're picking the neighborhood radii, we have to kind of get an idea of what that entails, because it's going to end up affecting our results. So basically, as you increase the radius, it's going to kind of act as a smoother. So if you look here, this is 12-kilometer radius, 30-kilometer, and 48-kilometer. And the colors are the actual probabilities from the model plotted. So as you increase the radius, you're losing some of the detail and gradients, and you're kind of relaxing the verification. So you're going to get more overlap between the neighborhood probabilities of the observed probabilities and the model probabilities, and it's going to actually increase your score or the skill of the model. However, if you increase it too much, you're losing detail in the actual forecast. So you're going to want to try to find a balance between the two. So here's some results from the actual neighborhood method. So this is 30 dBz reflectivity. So this is kind of correlates with where convection is, a threshold that kind of measures where convection is in the model. So if you actually look at the left graph here, both of these are 12 to 36 hours after initialization, and they're both averaged across 10 cases in both 2021 and 2022. So on the left side in the solid lines is 2022 at 4 different radii, and the dashed lines are 4 different radii in 2021. And you can see right away that 2022 seemed to perform better across most of the time period. On the right side is the actual differences calculated. So that dashed purple line is the actual zero, is the zero line. So anything above that, 2022 was superior. And you can see at pretty much all radii, it was superior, although that's not consistent across the entire time frame. So you could see a peak kind of toward the convective maximum of day 2, when there was probably more convective coverage, is when there was actually the most improvement in the model. And the other thing that I thought was kind of interesting here is the smaller radii, which is in red, that's 12 kilometers, versus the higher radii, the difference isn't as big. And that could be an indicator that maybe the biggest improvements in the model had more to do with synoptic forcing, or something that not so much involved with the actual cores of convection, because at 12 kilometers, you have a more detail in the model. So here's 2021 versus 2022, again, except with precipitation. So this is a threshold of 0.1 inches. So instead of 30 dBz, which kind of focuses on convection, this focuses more on just where the model produced precipitation in general with the 0.1 inch threshold. So this would also include things like stratoform precipitation. So you could see, again, pretty much an increase in all radii, except in this case, it's more consistent over time. And it's probably a bit more consistent over radii as well. And that's probably an indicator that it could be a similar indication to the last graph, where you basically have more of an improvement on the synoptic scale. So it's saying that there was a great improvement or large improvement in where the model was actually producing precipitation. But the improvement in actually producing convective cores was probably, while there was some increase, it wasn't quite as big of a jump. We also did 3 versus 10 ensembles in both 2021 and 2022. So these are actually comparisons between ensemble sizes, not between years. So in 2021, in both years, you could see that there was an increase in skill if you go to 10 ensembles from 3, which is not all that surprising. You have more ensembles, you generally have greater accuracy. However, particularly in the circled area, you can see that the differences aren't the same. There's actually a much greater improvement from 3 to 10 ensembles in 2022. And we hypothesized that that could have to do with the stochastic physics that was added to the 2022 model, which is basically a way of perturbing each of the individual ensembles throughout the run to increase ensemble spread. And when you have greater ensemble spread, you generally have greater forecasting capability if you increase ensemble size. Whereas on the left side, if you have more overlap in the ensembles, increasing the ensemble size isn't going to have as great of an effect. Now onto the severe surrogate method. So unlike the neighborhood method, the severe surrogate method, we're focusing exclusively on helicity tracks. So we're basically applying a threshold to the helicity tracks. It could be, in this case, it was 200 meters squared per second squared. And you're overlaying an 80-kilometer grid on top of the model. So in each 80-kilometer grid point, if you hit at that certain threshold, it's given a probability. And you can actually apply a smoother, sort of similar to the neighborhood method, that can vary in size. And that will actually cause overlap, so that when you plot it, instead of having zeros and ones on the plot, you'll have a spectrum of probability. And it almost looks like an SPC outlook. So if you look at the top here, this was applied to observed storm reports. And in the bottom, it was applied to the actual helicity tracks, and it's called a severe surrogate severe probabilistic forecast. So in this case, this was May 27, 2021. You could see that in the Midwest, it performed relatively well if you look at observed reports versus the model. But in the Northeast, there was a lot of wind reports on this day, whereas the model did not generate a whole lot of helicity. So at least by this method, the model did not do very well in the Northeast. So now to actually calculate this quantitatively, we looked at FSS, or fraction skill score, as well for the surrogate method. And we apply them in 2D plots. So the bottom is the amount of smoothing. So the amount of smoothing in kilometers, or the size of the radius. And the y-axis is helicity thresholds. So if you look at 2021, 2022, at first, they look kind of similar. There's not a whole lot of difference that you can pick out just by those two graphs. Although it does appear that though 2022 shifted a bit toward toward less smoothing. And if we actually look at the calculated differences, though, on the bottom here, so red is where 2021 was superior, blue is where 2022 was superior. And there's actually not it's surprising, because it's not really what we expected to see. It appears to be at first glance that actually better forecast capability in 2021, but these are kind of along higher helicity thresholds, which aren't all that common. And there is more improvement in 2022 toward lower smoothing, which could indicate that maybe there's slightly better placing of the actual helicity tracks versus where the storm reports, because you don't have to apply as much neighborhood smoothing. Another thing about this is we use the same 10 cases, but it's possible that this was not a large enough sample size for this. Because if you look at the variability in fraction skill score plots between 2021 and 2022, 2021 has a lot more variability, and there are 3 cases in particular, the bottom 2 down here and the one on the top right, that performed very well, that could be inflating the score of 2021 and basically not showing that there's an actual decrease in skill in 2022. There's also more consistency among the plots in 2022, which could be an indication of better forecast reliability. But it's really something I think we need to look into a little bit more, because I don't think there's enough cases to actually draw really good conclusions from this method. So just a couple conclusions here. So the standard neighborhood method basically showed greater skill in 2022 across multiple thresholds of both reflectivity and precipitation, which can indicate that 2022 produced more accurate forecasts both in accumulated precip and in simulated reflectivity. The largest scale differences between years occurred at lower thresholds and larger radii, which, even though we saw improvement in placement of the actual convection in 2022, is probably showing that the greatest improvement occurred more on a synoptic scale in terms of placing general features of precipitation and forcing. And we also saw greater differences between ensemble sizes in 2022, which again could indicate greater ensemble spread, which is promising. The sphere surrogate method, as I mentioned, is kind of more mixed, a little more gray. Overall, 2021 did show higher scores over a large range of view edge thresholds, but 2022 showed greater consistency among cases and higher skill score at lower thresholds. But again, I think we need to do a little more future work into this, because I really do think the case variability and just the differences in coverage on some of the case days. For example, 2021 had a few cases that were just very heavy in convection, produced a lot of convection. So I think we need to increase our sample size to get better results in this area. And that's about it, I think. Any questions? Yes.
So the thresholds that you compare with the radii that over the model,
Mhm.
do they fall out of demand naturally, or are they established in conjunction with anecdotal wisdom?
So actually picking the thresholds, it's more of what you're trying to focus on. So if you're looking at reflectivity, for example, and you want to see how well the model did at placing, let's say, convective cores, you could I actually did 40 dBz as well, which I didn't have time to show on here. So you kind of increase the reflectivity and you're going to have less coverage and really focusing on the core of the convection. If you decrease reflectivity to, let's say, 10 dBz, you'd be focusing on more of just where precipitation occurs in general. And the kind of substitute was the 0.1 inch accumulated precipitation, because that's a pretty low threshold. So that kind of showed just more of the general areas of precipitation. So it's based on what you're trying to look for, really, on how the model performs. Yes.
Talk about how the 2022 ensemble is better, at least for I think for the synoptic scale is a bit better.
Yeah. Oh, yeah, yeah.
Do you have thoughts on how you might improve the convective scale? Is it a matter of just having a finer grid spacing in your model to improve the prediction of scale?
I'm not sure. I'm not super familiar with how the FE3 actually works or generates convection, but
It's an ongoing. There's been a tremendous amount of development that's gone into place, partly facilitated by NWC to improve the skill model, and they've made quite a lot of progress with it. And I do think these results also reflect some of that progress too, but it is an ongoing issue. Okay.
yeah, I do think there certainly was still improvement on the convective scale as well. I just don't think it was as great as improvement on a broader scale, but there were improvement in both areas. Although at the moment, I still don't think it's as good as the HER, which is something I also want to do a little bit of data with. So we're getting there, but not quite ready to replace it yet. Thank you.
I'll try that before clicks.
Wow.
All right. Oh. First. Okay. Is it back to? Okay. Okay. How about now? Okay, there we go. It was a whole routine. I gotta get down. No. Come on. There we go. Okay. Thank you for bearing with us here. All right, our next speaker is gonna be Rachel Restel. She's a junior in atmospheric science, and she comes to us from the University of Louisiana at Monroe. And Rachel's gonna be talking to us about the analysis of mirrors, azimuthal shear observations of the morning QLCS mesovortices of 27 April 2011. So, Rachel, take it away.
Thank you for the introduction. Good morning, everyone. My research project for the summer analyzed the azimuthal shear observations of the 2011 super outbreak morning QLCS and its mesovortices. So before I jump right in, I'd like to give some terminology that's relevant and important to this study. First of all, QLCS stands for quasi-linear convective system. It's basically a line of storms associated with very fast and strong winds and typically short-lived and weaker tornadoes. A mesovortex is a small-scale, low-level rotational feature found within a QLCS. And azimuthal shear that I will be referring to as ash shear for the rest of this presentation, I learned the hard way from the 5-minute talk to give that abbreviation earlier than waiting until the middle. But in this study, low-level ash shear being recorded from the 0 to 3 kilometer layer and mid-level ash shear being recorded in the 3 to 6 kilometer layer are compared to one another, as shown in this plot of mesovortex H. And I just wanted to add that mesovortex H was actually the longest lived mesovortex and produced 2 EF3 tornadoes. Okay, so this morning QLCS was actually the first of the outbreak of the day. As you can see from the radar loop, there was a second one that followed it in the afternoon. So the morning QLCS actually formed on April 26th around 11:30 p.m. Central Daylight Time. And it produced a lot of stronger EF2 and EF3 tornadoes, making it an anomaly for a QLCS. It impacted the states of Louisiana, Mississippi, Alabama, Tennessee, Kentucky, Georgia, and Ohio with its tornadoes. So this study looked at the 47 tornadic mesovortices of the QLCS, and they were labeled alphabetically in the order of appearance. So this plot up here is a good example comparing the durations of each mesovortex to one another. And as you can see, as the QLCS began to dissipate and reach the end of its lifetime, the duration overall of the mesovortices got shorter. So in order to collect the ash shear values of the QLCS, they first had to be collected from the MIRS database. MIRS stands for Multi-Year Reanalysis of Remotely Sensed Storms, and it uses the WSR 88D archives in order to get this merged ash shear data. So MIRS can be thought of, looked at as like from a grid point of view, where if you're looking at one single point, the 4 closest WSR 88D radars scan the 0 to 3 kilometer layer and the 3 to 6 kilometer layer, looking for the highest ash shear value. And then that highest ash shear value that's found is used for the MIRS data. So once the ash shear data was collected from mirrors, it then had to be aligned. The 5-minute observation times were not the same as those of the radar detected times for each mesovortex. So once those were fixed and properly aligned, the 58 tornadoes in the QLCS were then went through, and the highest ash shear value was picked out, resulting in this table here with the mesovortex ID, the tornado number, if the mesovortex had more than one, followed by the rating. And then we also had the low level and mid-level maximum ash shear values found during the tornado with the associated hour, minute, and second that they were recorded. Then moving on to results, we mapped out all 47 mesovortices with their tracks and the 5-minute observation ash shear values as well for each point. So for those who can't really see the color bar here, the blue up to purple are the lower ash shear values, going up to the orange and yellow being the higher ash shear values. And from this zoomed in map of Mississippi and Alabama, the circled area of yellow is actually where the highest ash shear of the QLCS was recorded in mesovortex W at around 0.04 per second. So this QLCS actually had 4 total mesovortices that produced EF3 tornadoes. And in these plots here, they are compared, their ash shear values are compared to one another, with low level being on this top graph and mid level being on the bottom graph. And time of tornado genesis is also plotted along the bottom, color coded to the associated mesovortex. So these ash shear values for these 4 ranged as low as 0.0019 per second, all the way up to that highest value of the 0.04033 per second. So the highest value again was in mesovortex W, and that was found in low-level observations of ash shear. And the lowest value was found in the mid-level observations in mesovortex B. It was noticed with these 4 mesovortices, along with all of them not shown, that there are noticeable peaks in ash shear that happen immediately after or shortly following tornado genesis. And this pattern was also seen in a study done in 2019 of the Kankakee Valley mesovortices located in Northeast Illinois and Northwest Indiana, where in that case, peaks in ash shear happened immediately following tornado genesis. This study also looked to see if there were any patterns of ash shear dramatically increasing prior to tornado genesis, but results in this study did not show any pattern like that. Then ash shear was compared looking between weak versus strong tornadoes. Again, low level top violin plot, mid level being the bottom violin plot. There were a total of 37 weak tornadoes being rated EF0 and EF1, and 21 strong tornadoes being rated EF2 and EF3. So these results show that the maximum, median, and minimum values were all higher for stronger tornadoes, as was hypothesized at the beginning of this study. And the greatest difference between strong and weak tornadoes actually took place in the low-level observations, which was expected, knowing that mesovortices are lower-level features. Welch's t-test was run for these two cases, and the p-values from those were both less than 0.05, making these statistically significant, the significance of that will be explained later on. So again, weak versus strong tornadoes, ash shear values were compared, but this time comparing those to the mesovortices to those of the mesocyclones of the supercells from the outbreak. And that supercell ash shear data was collected from a study done in 2022 that just focused specifically on the supercells of the day. So once again, low-level ash shear comparisons are in the left violin plot, mid-level being in the right violin plot. And the differences that you see are between the median values from the supercells ash shear to those of the median values from the previous slide of the QLCS. So that greatest difference occurred between weak tornadoes and the mid-level observations. And that was a difference around 0.009 per second. Overall, the maximum and median values were all higher for the supercell tornadoes, which was also hypothesized in the beginning. And the same was true for the minimum values, all 4 except stronger tornadoes in the low-level observations, where the QLCS mesovortices actually had the highest minimum value in ash year. So Welch's t-tests were also run for these cases, and they were all less, p-values were also all less than 0.05. And I said I would explain the significance of that. It just means that overall there's a 95% confidence that these comparisons are statistically significant and were worth the time comparing and analyzing. So then going up, looking at the time a mesovortex formed until its first tornado occurred. For all tornadoes, regardless of rating, that average was about 12 minutes with a shorter median at about 8 minutes. And the longest time it took a tornado to form was 63 minutes. So minimum values, differences in time could not be determined because there were some cases where the radar detected time for mesovortex forming actually happened after tornadogenesis. And so further studies could be done trying to correct this and figure it out. But for this study, it could not be concluded. And then doing the same thing, but comparing these time differences for weak versus strong tornadoes. The average time for weak tornadoes was about 10 minutes, with stronger tornadoes higher at 15 minutes. The median values for weak tornadoes were at 6 minutes. Stronger tornadoes, again, longer at about 12.5 minutes. So looking at these results, stronger tornadoes overall took longer to form than weaker tornadoes. And so a Welch's t-test was also, I wanted to note, and despite stronger tornadoes taking longer to form, the maximum amount of time it took for a tornado to form actually happened for a weak tornado at 63 minutes, with the longest stronger tornado only taking 49 minutes. So a Welch's t-test was done for this case as well, and only came out at about an 85% confidence. So these were not statistically significant to one another. However, they're substantial enough to provoke further study comparing these lead times between weak versus strong tornadoes. And a study done in 2018 showed that the current lead time for tornadoes warned in advance is about 15 minutes. And from these results, you can see that if a forecaster waits until a mesovortex forms before they send out a warning, it will be too late for the public to react to that. So it would be good for forecasters to better anticipate mesovortex formation and be able to send out a warning before one forms to better inform the public. So further studies on that would be good as well. So that is all I have. Thank you very much for your attention. And I can take any questions now. I'll leave up the main points because I know that was a lot of information thrown at you. Yes.
So obviously, this deals with the radar coverage. Wondering if you happen to think about areas that have less dense radar coverage and how well it would work.
Yes, we wanted to, at the beginning of the summer, actually compare these ASHER values and look at the distance from the closest radar. We didn't have time to do that. So that was something I think would also be interesting in further studies, redoing this, comparing those with the distance from radar. But then again, we just didn't have time to do that in this study, but it's very important to ASHER. Any others? Yes.
What was your average radar update time?
It was 5-minute observation increments overall. All right, any others? Oh, and I forgot, I wanted to point out, I just figured out yesterday that this picture actually is credit to Daphne. I didn't know she took it, but when I put it on there, so I thought that was really cool. Thank you. Oh.
Hopefully that should be good. Alrighty. Our next speaker is going to be Lauren Harvey. Lauren is a junior in meteorology and is from Central Michigan University. Lauren will be talking about using the Tornado Tail Survey to measure warning reception and response during evening and nocturnal tornadoes. So, Lauren, it's all you.
Thank you so much. So good morning, everyone. I would like to start out with a question for the audience. So by show of hands, who here has experienced a tornado warning, or a severe storm they thought could produce a tornado? Yes, it's Norman, basically everyone. Well, guess what? You are all eligible to participate in the Tornado Tails survey. So what is Tornado Tails? It is there we go. It is a voluntary online survey run through NOAA's webpage that is available 24/7 year-round to anyone who has experienced a tornado warning, or a severe thunderstorm that they felt could produce a tornado. This survey, other than previous work, is designed to be taken immediately after the event. So instead of asking the hypothetical, what would you do during a tornado, we ask, what did you do? In addition, while most researchers need to wait a week or more out of respect for the victims of tornado events, this survey is designed to be taken immediately after the event at the participants' convenience. So previous work indicates that nocturnal tornadoes are disproportionately fatal events when compared to their daytime counterparts. Further, the percentage of deaths related to overnight events has risen between the 1960s to early 2000s. This is despite advances in tornado forecasting, warning sources, and public education. So the real question is, why is this occurring? There are two possible answers. This could be a warning dissemination, warning reception gap, or it could be a warning reception, warning response gap. Previous work has also indicated that people are far less confident in their ability to be notified of tornado warnings during overnight hours. This is an issue because Lindell and Perry's protective action decision model, which follows people's decision-making between warning reception and protective actions, suggests that an outside influence is needed to begin decision-making. Further, the message must be understood and the potential threat must be seen as a hazard. So to look into this question, we first went through the data from the first iteration of the Tornado Tails survey. This is about 500 responses in total. False and/or repetitive responses were eliminated, and 3 statistically significant events were identified. The reports for these events were limited to ±1 day and within the same state to account for variability. The 3 events selected were the April 29th, 2022 Andover, Kansas tornado that occurred at 8:10 p.m. local time, the June 8th, 2022 Overland Park, Kansas and Buckner, Missouri tornadoes, which occurred at 1:10 and 1:37 a.m. respectively, and the February 26th, 2023 tornado that occurred in Norman, Oklahoma at 9:13 p.m. So from this data, we took the geospatial locations of each respondent and put them on an ArcGIS map. So here we have the tornado polygons in red from the Iowa Environmental Mesonet. We have the tornado paths in black from the NOAA Damage Assessment Toolkit, and we have responses in the vector points here in multicolors. The blue lines here are 10 miles for scale. Further, our quantitative data was analyzed via 1-0 coding and chi-squared testing for significance. All of the results that I will be presenting were statistically significant at the 95% level. Our qualitative data from our open-ended responses were analyzed for common themes related to the protective action decision model, as mentioned previously, the concept of milling, which is the idea that people will look towards others to determine if a threat is an actual hazard and what they should do about it, and the idea of transformational learning and critical reflection,
This is the idea that adults can change their perception of the world based on real life experiences. So what did we find? For warning reception, we found that only 72% of people from the June 8th event that occurred in the early morning hours actually received a warning. This is compared to 88% for the April 29th event and 100% for the February 26th event. There are really two possible explanations that I looked into for this. One possibility is that people were sleeping or otherwise not paying attention to the weather during these overnight hours. This severely limits their ability to receive warnings, as really automated text alerts and sirens are the only available warnings for people who are asleep. Further, there was an 11-minute gap between tornado touchdown and warning issuance for the Overland Park tornado in specific. This meant that some people did not receive warnings for the storm. And we had multiple indications from our open-ended responses that people saw the storm before the tornado sirens went off. Further, automated texts and sirens were the most common response sources for warning reception. This is likely due to the automated nature of these sources. The end user does not have to go looking for information like they would for the internet or social media. Instead, the information is directly taken for them. So now people have received a response. How do they respond to that warning? Out of all participants, 88% of April 29th, 22 participants indicated that they took a protective action during the event, whereas only 69% of June 8th, 2022 participants took some type of protective action. Out of everyone from the February 26th, 2023 event, 100% of people responded that they had taken a protective action. Now, this may look like the people from the June 8th event were being complacent, that they did not care that the tornado warning was occurring. However, if we look specifically at those who received warnings, out of people who received warnings, 100% of people from the April 29th event took a protective action, alongside 94% of people from the June 8th event. Out of the 3 people who did not take a protective action, 2 of them indicated that they did not receive a warning in time to protect themselves. Only 1 person out of the entire event indicated that they did in fact receive a warning, but did not take a protective action. This shows that there is very little complacency among participants in our survey. So another potential problem is that people are not understanding what they need to do during a tornado warning. However, we found that most people were indicating that they were moving themselves or their family to the most secure area at their location. Also, most of our participants were at home in stick-built houses during this time. So this follows National Weather Center guidance to move to the most secure location, such as an interior closet or a basement. So this shows that people generally do know what they need to do during a tornado warning, and they are willing to take protective action. So, to sum up my key points, a higher proportion of respondents received warnings during the evening events in comparison to the early morning event, likely because participants in the early morning event were either sleeping or failed to receive a warning due to issues with warning dissemination. Further, automated text alerts were the most common warning source during every event, followed by sirens. This is possibly due to the automated nature of these warning sources. And when differences in warning reception are accounted for, there's little difference in the proportion of people taking protective action. This indicates that there is not much complacency between these participants. Finally, moving oneself and one's family to a secure location were the most frequently reported protective actions, which indicate that people do generally know how to protect themselves and their families during tornadic events. So in conclusion, the discrepancy in nocturnal tornado fatality rates as compared to daytime events may be more strongly influenced by issues with warning dissemination and reception, rather than by issues with complacency or lack of sheltering knowledge. For more information about this survey, we did create a story map here, so you can actually go see how people were responding through their open-ended responses. Now I'll take any questions.
go back to the slide that showed where people were receiving information.
I don't think the keys are working. Oh, the arrow keys? Yeah.
You may see the clip in the window.
Oh, is it working now? Yeah. Okay. Yeah, I think we're good. So you said the warning sources?
Yeah. Did you look at the why? I just found this interesting that Norman had such a high social media, whereas everyone else didn't.
Yeah, so they were wondering why Norman had such a high social media account compared to other sources. So one potential factor, at least for the June 8th event, which is here in like the medium green color, would be that people are just not checking social media. However, between the April 29th and February 26th event, we didn't specifically look at that. But my best guess is that Norman is a very weather aware community. So people are going to be sharing weather information via social media much more than, say, Andover, Kansas.
And we also know why TV was also.
Yeah, that's probably for a similar reason. Yeah.
Were you able to find out about like the background of the participants to know if they work in like a career related to weather and that's why maybe they know the survey, or if it was more just your average person that was taking the survey?
Yeah, so we didn't specifically ask for careers or education levels. However, some people did volunteer in the open-ended response that they were storm chasers or degreed meteorologists or had an interest in weather. So a few of those people responded, but it wasn't really enough to look into to say, like, these people were receiving more warnings, for example.
Were the tornado warnings the same or different on the scale?
So they were different. I believe the strongest tornado we had was the Andover tornado. If I remember correctly, that was an EF3. But I believe they varied from EF0 to EF3.
Speaker.
Okay, let's just give another round of applause for all of our speakers. Thanks, Monique. So this concludes our final talks for the REU, NWC REU and the AI2ES programs. I know you all put in a lot of work this summer and it's showed in all of your presentations. I'm always really impressed from your 30-second talks to your 5-minute talks to now, just like you might not see the progression, but the mentors and Daphne and I definitely see that. So for sure, impressed by all of the work that you've done. Thank you to our moderators yesterday and today for helping us run smoothly and getting all of the things shared, even though we had some technical difficulties. And thanks to our audience too, both in person and online for joining us today. I also want to give a special thanks to Daphne, Amy, and Susan for helping put together all of the pieces and helping the program run smoothly. And NSF for their continuous support and funding of our program. Finally, I'd like to thank our mentors and their affiliations. We definitely could not run the program without all of your support. We have CAPS, CERO, NSSL, ARC, SPC, the Oklahoma Mesonet, OCS, IPRA, AI2ES, and from the University of Oklahoma, we have the School of Meteorology, Computer Science, and Department of Communications. Again, programs like these would not be able to run without all of your support. So I'm glad we're able to host this. and look forward to getting these recordings up online and having our final week next week. Thank you so much.